Hello there, and welcome to Physics with William, where curiosity gets comfortable and science takes its time. Tonight we are turning our attention towards something tiny, elusive, and just strange enough to make even a seasoned physicist pause for a moment and smile. Our subject is the positron, a particle that sounds at first like it ought to be cheerful and well-behaved, perhaps the sort of thing that arrives early, keeps tidy notes, and never causes any trouble. In truth, it is far more interesting than that. It is familiar and alien at once. It behaves in ways we can measure with extraordinary precision, and yet the moment we ask what it really is, what it is truly made of, the ground beneath the question begins to shift a little. Before we settle into that puzzle, I would love to know where in the world you are listening from tonight. Are you tucked away in a quiet room while the rest of the house has gone still? Are you wearing headphones on a late train, watching the dark slip by the window? Are you listening from a city full of lights, or a place where the night sky still looks properly ancient? And, since it feels fitting for an evening spent with physics, what is the hour where you are right now? Somewhere, it is deep midnight. Somewhere else, dawn is only just beginning to gather itself. And here we all are, arriving at the same question from our own little corners of the world. If you find this gentle wander through science soothing, interesting, or simply a pleasant way to unwind, I would be very grateful if you gave the video a like and maybe subscribed. It helps this quiet corner reach other people who might enjoy a slower way of thinking about the universe. And with a topic like this one, there is a good chance that somewhere out there someone else is also lying awake wondering how something can exist, carry mass, carry charge, behave exactly like a known particle in almost every way, and yet somehow still be its opposite. Physics has a way of producing questions like that, very small questions that open into very large rooms. So let us begin slowly. At first glance, the positron sounds almost like a joke nature might tell when it is feeling particularly clever. If the electron is one of the basic ingredients of ordinary matter, a tiny particle woven into atoms, electricity, chemistry, and the whole untidy business of material existence, then the positron is in some sense its mirror partner. It has the same mass as an electron. It has the same amount of spin. It responds to forces in almost exactly the same way. But its electric charge is reversed. Where the electron is negative, the positron is positive. That one change might sound modest, almost cosmetic, a simple matter of sign. But in physics, a reverse charge changes everything about how a particle behaves in the company of others. It changes what it is attracted to, what it is repelled by, how it moves through matter, and what happens when it meets its counterpart. And that meeting, as we will come to see later, is not especially peaceful. Still, before we rush toward dramatic endings and vanished particles, it helps to stay with the first question. What is a positron really made of? It sounds like a simple question because it belongs to a family of questions we've been asking for a very long time. What is wood made of? What is water made of? What is air made of? What are stars made of? Human beings have always been drawn to these nested layers of reality. The sense that if we keep opening the boxes, one inside another, we will eventually arrive at the final contents, the true little lumps from which everything else is built. That instinct has served science very well, at least for a while. We once thought substances were continuous, smooth all the way down. Then came atoms. We once thought atoms were indivisible. Then came electrons and nuclei. We once thought nuclei were perhaps the last stop. Then came protons and neutrons and later quarks. Every time we imagine we have reached bedrock, nature has a habit of producing a trapdoor. So it is natural to ask the same of the positron. If it is a particle, is it made of smaller pieces? Does it contain something hidden inside it, some deeper structure, some more basic machinery? Is it a tiny object with components? Is it a little bead of something? Is it a knot in a field? Is it condensed energy? Is it truly fundamental, which is the physicist's polite way of saying, as far as we can tell, there are no smaller bits rattling around inside? and already we've arrived at one of the subtle tricks of modern physics. The deeper the question becomes, the less useful everyday language starts to feel. When we ask what a chair is made of, we know roughly what sort of answer we are expecting. Wood, metal, screws, fabric, perhaps a regrettable design choice or two. But when we ask what a particle is made of, we are borrowing language from the world of furniture and soup and applying it to a domain where the usual assumptions no longer hold. To be made of something usually means to have parts. Parts that could in principle be separated, rearranged, counted. Yet some of the entities in modern physics do not behave as though they are assembled in that ordinary way. They are not miniature versions of visible objects. They are not tiny billiard balls with surfaces and interiors. They belong to a level of description where the universe is less solid, less intuitive, and much more dependent on relationships, properties, and fields than on little hard pieces. This is one of the reasons the positron is such a satisfying topic. It invites the kind of question a child might ask with complete seriousness and excellent timing. What is it made of? But the honest answer turns out to require some of the best ideas in 20th century physics, along with a willingness to let go of certain comforting pictures. It asks us to move from the old instinct that reality must be built like a machine into a stranger possibility, that what we call a particle may be less like a tiny object and more like a stable event in a deeper fabric. That sounds lofty if stated too quickly, so let us keep our feet on the ground for a little longer. The electron by now feels almost domestic. It appears in schoolbooks, diagrams of atoms, electric circuits, and every explanation of why chemistry works. It is everywhere, so much so that it has become mentally ordinary. But there is something remarkable about the fact that nature allows another particle that matches it so closely while carrying the opposite charge. The positron is not just similar to the electron. In many respects, it is the electron's equal and opposite twin. If you were to list the electron's basic measurable traits and then flip the sign of the charge, you would be most of the way there. And this raises an unsettling possibility. If a particle and its opposite can both exist, then perhaps the universe is more symmetrical than it first appears. Perhaps matter, which feels so normal to us, is not the only way the ingredients of reality could have been arranged. Perhaps our world is only one side of a deeper pattern, and the positron is one of the places where that pattern peeks through. There is also something faintly humorous in how calmly the positron sits inside serious physics. In daily life, if someone told you that every ordinary particle might have an oppositely charged counterpart, and that when the two meet they can disappear in a burst of energy, you might suspect they had either been reading too much science fiction, or perhaps had not slept properly. In physics, however, this is not only acceptable, it is textbook material. Students learn it, hospitals use it, experiments depend on it. The universe can become astonishingly strange and then, after a few decades of measurements and practical applications, settle into routine. One of the quiet miracles of science is how it takes the deeply bizarre and teaches us to treat it with matter-of-fact confidence. Yet even when a thing becomes familiar in the laboratory, it does not lose its philosophical bite. The positron still presses on basic questions. If it is real, and it is, what kind of reality does it have? If it can be created from energy under the right conditions, what does that say about the relationship between particles and process? If it can vanish in an encounter with an electron, what becomes of the idea that matter is made of enduring stuff? And if the best description of it comes not from imagining a tiny object but from understanding an excitation of a quantum field, then maybe the phrase "what is it made of" is not wrong exactly, but incomplete. I think this is where physics becomes especially good company late at night. It does not merely hand us facts to memorize, it gently retrains the mind. It teaches us that some questions must be refined before they can be answered. Not discarded, not mocked, simply sharpened. The childlike question remains valuable, but the universe sometimes answers in a language that takes patience to learn. So let us approach the positron the same way we might approach an unfamiliar animal glimpsed at the edge of a forest. Not by charging at it with definitions, but by observing what it does, where it appears, how it behaves, and what patterns follow it. In science, behaviour often reveals essence more reliably than appearances do. We may not be able to take a positron apart with a tiny screwdriver and inspect its internal shelves, but we can study how it moves in electric and magnetic fields. We can track how it is born. We can watch how long it survives in matter. We can detect the radiation produced when it meets an electron. We can compare theory and experiment to ridiculous levels of precision and see whether our picture holds. And from all that, a portrait begins to emerge. The portrait, though, is not the one common sense expects. Common sense prefers objects that endure, objects that exist in the same straightforward way whether or not they're interacting. Classical thinking likes little particles travelling along clear paths through a stable background. Quantum physics is less accommodating. It tells us that the world at small scales is not just hidden from ordinary sight, but organised according to principles that do not map neatly onto daily intuition. In that world, particles are not always best pictured as little pellets. Identity is tied to properties more than to substance in the old sense. Creation and destruction are built into the rules. What persists are not tiny marbles, but patterns described with astonishing mathematical precision. The positron sits right in the middle of that modern picture. It is not exotic in the sense of being rare only in some distant corner of the cosmos. Positrons can appear in radioactive processes, in particle interactions, in cosmic rays, and in technologies used to peer inside the human body. They are quite real, quite measurable, and quite useful. But conceptually they are a doorway. Once you take them seriously, some older ideas about what matter must be like begin to loosen. One way to feel the strangeness properly is to notice how language tries to rescue us. We hear that the positron is antimatter, and for a moment that sounds like an explanation. But it is really a label for the mystery, not its solution. To call something antimatter tells us how it relates to ordinary matter, not what it is in itself. Likewise, to say it is the electron's antiparticle is correct and important, but still leaves the deeper question waiting politely in the corner. Yes, but what kind of thing is an antiparticle? What does it mean for reality to come in such pairs? Why should the world have this sort of bookkeeping at all? There is an old temptation, when faced with such questions, to imagine hidden little mechanisms just beyond our current reach. Perhaps the positron is made of even smaller things that explain its properties, the way gears explain the motion of a clock. Sometimes that instinct has been right in the history of science. Bigger structures often do contain smaller structures, but sometimes nature appears to stop offering deeper mechanical pieces and instead offers a different style of explanation entirely. The explanation becomes, not this object contains these smaller components, but this object is a basic excitation of an underlying field, and its properties arise from the structure of the theory itself. That answer can feel unsatisfying at first, because it sounds less like opening a box and more like learning a grammar. Still, grammars can be profound things. A sentence is not made of meaning in the way a table is made of wood. Its significance arises from structure, relation, and rule. In a somewhat analogous way, a particle in modern physics may not be made of smaller chunks in the old intuitive sense, but may instead be an allowed stable pattern in a deeper set of fields and symmetries. The positron, then, is not a tiny ball of positive stuff packed around a core of mystery. It is a specific kind of entity permitted by the architecture of the universe. That may sound cold if put too bluntly, but I do not think it is. In fact, I think it is rather beautiful once the mind adjusts. It means the universe is not merely a heap of ingredients. It is a system of possibilities, some of which become actual in wonderfully precise ways. The positron is one of those possibilities. Not an accident, not a loophole, but something the laws themselves appear to require once the deeper structure is taken seriously. And here a quiet historical irony begins to hover in the background. The positron was not first discovered because someone had a jar full of them and wondered what to call the contents. It emerged from theory before it was confirmed in experiment. That is one of the deliciously unsettling episodes in modern physics. Human beings wrote down equations in trying to describe known particles more accurately, and the mathematics pointed toward the existence of a partner that had not yet been seen. Imagine drawing a map of a coastline you know well, and finding by sheer logical necessity that there must be an island offshore. Then later, someone sails out and finds it. Physics occasionally does that. It reasons beyond experience and then reality, with an almost mischievous smile agrees. We will come in due course to how that happened and why it mattered so much, because it changed more than one particle inventory. It changed the scientific imagination. It suggested that nature was deeper, more symmetric, and in some ways more conceptually daring than many had expected. It also showed that asking what a thing is made of sometimes leads not to a pile of ingredients, but to a new framework altogether. For now, though, it is enough to sit with the question and let it become sharper. What is a positron really made of? If you ask in the style of ancient atomism, you may be disappointed. If you ask in the style of modern field theory, the answer becomes more subtle and, I think, more satisfying. A positron does not seem to be made of smaller parts in the way a molecule is made of atoms. As far as current evidence goes, it behaves as an elementary particle. That does not mean it is simple in the everyday sense. It means that, within our best present description, it is not composite. We do not detect internal structure. We do not see signs that it contains more fundamental subunits. When probed at extremely small scales, it continues to behave as though it is point-like, fundamental, a basic unit of the theory. But even that statement must be held gently, because in physics, fundamental usually means fundamental so far. Science is honest enough to leave the door ajar. We work with the best evidence available. We do not mistake current success for eternal finality. There may someday be a deeper theory in which even particles we now call elementary turn out to be aspects of something more underlying. Physics has surprised itself before. It may do so again. Yet within the framework that presently describes the world with astonishing success, the positron is not built from smaller ingredients. It is one of the ingredients, and that brings us to a lovely tension. We ask what the positron is made of because we assume reality should end in pieces. Modern physics, at least for now, replies that perhaps reality ends in fields, symmetries, and quantized excitations. The old image of substance gives way to a more dynamic image of event and relation. The positron is not an object assembled out of hidden parts like a watch or a walnut. It is more like a stable note the universe is able to play. I realise that image risks sounding more lyrical than useful, so let me anchor it again. If you pluck a violin string, the note is real, measurable, and has definite properties, but it is not made of tiny note particles packed together in the string. It is a pattern the system can support. Likewise, though not exactly likewise, the positron may be better understood not as a miniature positive bead, but as a definite quantum excitation of an underlying electron field. Same field, opposite charge, same mass, different role in interaction. Already we are inching toward the deeper answer, the one modern physics prefers. Not made of smaller lumps, but arising as a specific allowed state of a more fundamental field. That change in perspective can feel almost too abstract at first, especially when one is used to asking what things are made of in the ordinary tactile sense. But physics often asks us to trade the comfort of familiar pictures for the power of accurate ones. And when it does, the reward is considerable. Once you begin to think in terms of fields rather than little solid pellets, the existence of the positron stops feeling like a magical exception and starts feeling like part of a coherent pattern. A strange pattern, yes, but no longer an arbitrary one. So this is where we have arrived for tonight. Not at a final answer delivered with a thump, but at the opening of the right kind of door. We have met the positron not as a curiosity from the margins, but as a serious clue about how the world is organised. We have seen that the simple-sounding question of what it is made of leads us toward deeper questions about particles, fields, symmetry, and what it even means for something to be fundamental. And from here, the next step is a natural one. If the positron is so closely related to the electron, if it is not simply a made-up bookkeeping trick but a real physical entity, then the story of how it first entered science becomes impossible to resist, because before anyone could ask what it was made of, someone had to realise that nature might contain such a thing at all, and that realisation did not come from a microscope so much as from a theory daring enough to predict a particle the world had not yet revealed. If the positron now seems like a respectable member of physics, calm in the textbook and perfectly at home in a particle detector, it is worth remembering that its arrival was anything but ordinary. It did not stroll politely into science carrying a name tag and a tidy summary of its intentions. It arrived through a mismatch between what older intuition expected and what newer theory insisted might be possible. And for a while, even very clever people were not quite sure what to make of it. That is often how important discoveries begin, not with a trumpet blast, but with a discomfort. Something refuses to fit, something looks wrong, then wrong in a very consistent way, and eventually wrong enough that reality itself has to be taken more seriously than habit. By the early years of the 20th century, the electron was already well established. It had gone from being a strange newcomer to a central player in modern physics. It explained electricity. It helped make sense of atoms. It sat firmly inside the emerging picture of matter. Scientists had learned to measure its charge and mass with increasing confidence. They knew it was small, light, and negative. It was no longer speculative. It was real in the laboratory and powerful in theory. Once that happened, the temptation was to imagine that the basic cast of characters was becoming familiar. Perhaps there would be a few new details, a few new interactions, maybe a better mathematical treatment here and there, but surely the universe was not going to spring a perfect opposite on them and ask everyone to remain composed. And yet that is nearly what happened. One of the central figures in this story was Paul Dirac, a physicist with a mind so exact that even other physicists sometimes spoke of him as though he belonged to a different species of calm. Dirac was not interested in noisy speculation or decorative language. He liked precision. He liked clean mathematical structure. He liked equations that behaved properly and theories that made sense even when no one was watching. In the late 1920s, physics was wrestling with a major problem. Quantum mechanics had achieved impressive success in describing atoms and small-scale behaviour, but it was not yet comfortably aligned with special relativity. The world of the very small and the world of a high-speed motion were both real, both well supported, and not yet speaking as fluently to one another as one might hope. Dirac set out to change that. He wanted a theory of the electron that respected both quantum mechanics and relativity. This was not a decorative exercise, it was a demand for consistency. If electrons could move at speeds where relativity mattered, then a proper theory had to account for that from the start, not tack it on afterward like an awkward correction. Dirac worked with the sort of confidence that comes from following logic very closely. He was not guessing at new particles. He was trying to write down a better description of a known one, and then the mathematics did something unsettling. When Dirac found his new equation for the electron, it did not merely describe the expected states. It also seemed to allow solutions with negative energy. This was a problem, and not the pleasant kind of problem that leads to applause. In ordinary thinking, energy should not simply drop without limit. If particles could always tumble down into lower and lower negative energy states, the world would become wildly unstable. Electrons ought to cascade into these states endlessly, which very plainly does not happen. So Dirac faced a puzzle. His equation was beautiful and powerful, but it seemed to come with a strange and unwanted extra. At this point, many scientists might have been tempted to treat the odd solutions as mathematical rubbish, the sort of debris that sometimes appears in a calculation and can be swept aside with a stern face and a strong cup of tea. But Dirac did not dismiss them so quickly. He had enough faith in the structure of the theory to suspect that the trouble might not be in the mathematics, it might be in the interpretation. This is one of the great habits of theoretical physics at its best. When a serious and elegant theory produces something unexpected, the right response is not always to force the theory back into old expectations. Sometimes the better move is to ask whether nature is stranger than the expectation. Dirac proposed an interpretation that was daring, and at the time rather odd. He imagined that the negative energy states were all filled in a kind of invisible sea. Because of the rules of quantum mechanics, ordinary electrons could not simply fall into these filled states. They were already occupied. This move rescued stability, but it created a new idea. If one of those negative energy states was somehow emptied, the absence would behave like a particle with positive charge. In other words, a hole in this sea would act as the opposite of an electron. It is difficult to overstate how peculiar this must have sounded. A hole behaving like a particle is already a conceptual stretch for common sense. A positively charged counterpart to the electron was even more dramatic. Dirac at first wondered whether this opposite particle might actually be the proton, since the proton was known and positively charged. But that possibility did not hold together. The proton is much heavier than the electron. Dirac's theory pointed towards something with the same mass as the electron, not a completely different one. The mathematics was not asking for a heavy positive particle, already familiar from atomic nuclei. It was asking for a mirror electron. That was the daring idea. Not a revised electron, not a bookkeeping trick, not a reinterpretation of the proton. A new particle, same mass, opposite charge. At first, many physicists were cautious. That caution was not unreasonable. Physics had already become strange enough without adding an exact positive counterpart to a known particle, and in any case, theory alone does not close the matter. You can admire a theoretical structure and still want the world itself to sign the document. Predictions need evidence. Nature has the final word, however softly delivered. So the search moved from mathematics toward experiment. This is where the atmosphere changes from chalkboards and abstract reasoning to the more improvised world of cloud chambers, cosmic rays, and careful observation. Before particle accelerators became the dominant engines of discovery, much of high-energy physics relied on radiation arriving from space. Cosmic rays were constantly striking the atmosphere and producing showers of energetic particles. If one had the right apparatus and enough patience, the sky could become a laboratory. A cloud chamber was one of those wonderful devices that sounds almost magical until you understand it, and then somehow becomes more impressive. It allowed charged particles moving through a supersaturated vapor to leave visible tracks. Tiny droplets would condense along the path, so invisible subatomic events could be turned into delicate lines that photographers and physicists could study. Suddenly, the behavior of particles was no longer entirely hidden. They wrote on the air. Carl Anderson, an experimental physicist working in California, was using a cloud chamber in the early 1930s to study cosmic rays. He placed the chamber in a magnetic field, which caused charged particles to bend. The direction of the bend revealed the sign of the charge, and the amount of curvature gave clues about the momentum. This was not glamorous work in the cinematic sense. It was careful, patient, and interpretive. A cloud chamber image is not a labeled diagram from a textbook. It is a clue, a trail, a piece of physical handwriting that must be read correctly. In 1932, Anderson observed a track that did not fit the expected pattern. It looked like the path of an electron in many respects, especially in the way it curved and in what it implied about the mass, but the direction of curvature indicated a positive charge, not a negative one. It was as though the chamber had calmly written down a contradiction and left the humans to sort it out. This mattered because one could imagine various ways to misread a single event. Instruments can deceive, tracks can be ambiguous, radiation is messy. So the question was whether this strange path truly represented a new particle, or some familiar particle behaving inconveniently. Anderson approached the matter carefully. He used a lead plate inside the chamber so that particles passing through would lose energy. This helped determine which direction the particle had travelled. Once that was understood, the curvature could be interpreted correctly. And there it was, again. The track belonged to a positively charged particle, with a mass much closer to that of the electron than to that of the proton. In effect, the universe had signed the document. Anderson called the new particle the positron. The name was neat and direct, which was fortunate because the underlying idea was strange enough already. Here was the first discovered antiparticle, the first clear evidence that a known particle could have a partner equal in mass and opposite in charge. Dirac had found the possibility in theory. Anderson had found the thing itself in experiment. Between them, the old picture of matter became harder to maintain in its familiar form. What is especially fascinating about this episode is how different the two halves of the discovery feel. On one side, a theorist pursuing consistency in the mathematics of the electron. On the other, an experimentalist studying tracks in a cloud chamber. One begins with logical structure, the other with photographic evidence. One says nature ought to contain such a particle if the theory is right. The other says nature does contain it, and here is the mark it left. Neither side is sufficient alone. Together they create one of the most satisfying moments in science, when thought and world meet without either having to pretend the other does not matter. There was also a wider significance that people quickly began to appreciate. The positron was not just another addition to the particle list. It was evidence for a new principle about the structure of reality. If the electron had an opposite partner, then perhaps other particles might as well. Matter was no longer the only game in town. There could be antimatter, a whole shadow inventory of partners corresponding to the familiar ingredients of the material world. That possibility changed the imagination of physics. It opened doors toward new interactions, new symmetries, new questions about the early universe, and new puzzles about why ordinary matter seems to dominate the cosmos we see. Still, it is helpful not to leap too far ahead. At the moment of discovery, there was still plenty to digest. Physicists had to learn what the positron actually did in matter, how it was produced, how it interacted, how it could be distinguished reliably from other particles, and how its existence fit into the broader emerging framework of quantum field theory. This was not a one-day shift from disbelief to mastery. Science rarely works that way. There is usually a phase in which the new object is real but not yet domesticated. People know it exists. They do not yet know how comfortable they are going to be with all its implications. The positron went through that phase, though it did not stay there for long. More evidence accumulated. Other experiments confirmed its properties. It was produced in pair creation events. It showed the expected behaviour in electromagnetic fields. When it encountered an electron under the right conditions, both could disappear and produce radiation in a process that made clear this was no mere curiosity. The positron belonged inside the structure of the theory. It was woven into the same deep rules that governed the electron and light. There is a subtle emotional shift in this kind of discovery that I think is easy to miss when reading the clean version in hindsight. At first, a strange theoretical prediction feels like a problem. Then a puzzling experimental trace appears and seems almost annoying in its refusal to behave. But once the pattern locks into place, once the theory and experiment support one another, the mood changes from suspicion to relief. The universe is strange, yes, but it is not random. The oddness has order. The positron is not nonsense. It is a clue that the world is more systematic than old intuition had allowed. I also think the discovery says something important about the style of modern physics. It is not merely a collection of measurements, nor merely a game of elegant equations. It is a discipline in which deep structure can reveal entities before they are seen, and careful observation can rescue abstractions from sounding like fantasy. The positron is a perfect example. Had Dirac only predicted it, people might remember it as an interesting theoretical detour. Had Anderson only seen a strange track with no theoretical framework waiting for it, the interpretation might have taken longer to settle. Instead, each side gave the other strength. There is also a more human detail here. Discoveries of this kind remind us that progress in physics does not always come from looking directly for something new. Dirac was not setting out to invent antimatter as a dramatic flourish. Anderson was not necessarily expecting to photograph nature's mirror electron on a given afternoon. Both were doing something more ordinary and more admirable. They were taking existing questions seriously and following the consequences without flinching too soon. That is often where the real surprises live. Not in theatrical guessing, but in disciplined attention. Once the positron was accepted, the old question of what counts as matter began to look less settled. If there can be a particle so much like the electron, and yet opposite in charge, then the category of particle identity is not just a list of familiar objects. It is bound up with symmetry, transformation, and the deeper rules by which fields are allowed to exist. The positron was not simply a spare part nature had forgotten to mention earlier. It was a sign that the architecture of the universe includes mirrored possibilities, and yet the discovery did not make the positron feel unreal or ghostly. Quite the opposite. It made it concrete. One of the reassuring features of experimental physics is that it keeps the grandest ideas grounded in apparatus, materials, tracks, and measurements. A positron is not an airy philosophical possibility. It bends in a magnetic field. It leaves a trace. It can be produced and detected. It can be used in medicine. It behaves according to laws that can be tested over and over again. Strange does not mean vague. Physics is at its best when it gives us things that are both deeply counterintuitive and sharply measurable. There is a mild comedy in this too. Humanity spent centuries trying to understand matter, and once we reached the modern era, the universe responded by saying that the small negatively charged particle you already know has a positive twin. And by the way, they can wipe each other out in a flash of radiation. This is the sort of detail one would reject in a novel for being too neat, and yet reality seems untroubled by such literary concerns. What matters for us now is that the discovery of the positron did more than reveal a new particle. It changed the question we have to ask next. Once nature's mirror electron was found, it was no longer enough to marvel at its existence. The next issue became more precise. If this new particle matched the electron so closely, if it had the same mass and spin and obeyed the same broad rules of motion, what exactly was the difference between them beyond the sign of the charge? Was that one reversal the whole story, or did it point towards something deeper about identity, interaction, and the way particles are defined in the first place? That is where the trail naturally leads. Because once the mirror has been discovered, one begins to notice not only the resemblance, but also the exact feature that turns reflection into opposition. Once the positron had been recognized as real, the next question became almost unavoidable. If it resembles the electron so closely, what actually makes it different? At first, the answer seems so small that it almost feels disappointing. The positron has the same mass as the electron. It has the same spin. It responds to the same electromagnetic rules. It can move through fields in ways that mirror the electron almost perfectly. In many calculations, you can take the description of an electron, reverse a few key properties, and arrive at the positron. So the temptation is to say that the only difference is the sign of the electric charge and leave it there. But in physics, a small change in a basic property is not a small change in consequences. A reversed charge is not like changing the colour of a shirt or the name on a label. It changes how the particle fits into the entire structure of matter. It changes what it is attracted to, what it is repelled by, what sort of bound states it can form, how it behaves in ordinary material, and what happens when it encounters its counterpart. The electron and the positron are like two entities that follow the same rules of motion, carry the same amount of inertia, and yet are assigned opposite roles in the electrical life of the universe. That one reversal is enough to separate worlds. It helps to begin with the similarities, because they are so exact that they deserve respect. The positron is not a heavier cousin of the electron. It is not a rough imitation. It is not an unstable version with a slightly altered internal recipe. As far as our best theories and experiments tell us, it has exactly the same mass as the electron. If you place the two in the same kind of magnetic or electric setup and observed how strongly their inertia resisted acceleration, the mass itself would not distinguish them. The same is true of spin, which is one of the intrinsic quantum properties particles carry. The positron has the same spin value as the electron. It is a fermion, just as the electron is. It obeys the same broad statistical rules that govern matter particles of that type. This point matters because it means the difference between them does not come from size, bulk, or some extra hidden complexity. If one were larger, heavier, or structurally more elaborate, the comparison would feel almost ordinary. Instead, nature has done something stranger. It has created a partner that matches the electron in every essential mechanical sense, while reversing a set of relational properties that determine how it interacts with the rest of the world. The most obvious of those relational properties is electric charge. The electron is negative. The positron is positive by exactly the same amount. That exactness is important. It is not approximately opposite. It is not mostly opposite, with some slight correction tucked away in the decimal places. The magnitudes match. If the electron carries 1 unit of negative electric charge, the positron carries 1 unit of positive electric charge. This is what makes the positron the electron's antiparticle, and not merely another positively charged particle. A proton is also positive, but it is not the electron's antiparticle, because its mass and internal structure are entirely different. The positron fits the role because it mirrors the electron in all the right ways and opposes it in the defining ones. From that single difference in charge, a long chain of consequences follows. In an electric field, an electron accelerates one way and a positron accelerates the other. Near an atomic nucleus, which is positively charged, the electron is attracted and the positron is repelled. That alone makes their behaviour in ordinary matter dramatically different. Electrons are perfectly at home in atoms. In fact, atoms as we know them depend on electrons being bound around nuclei. Chemistry depends on that arrangement. Solids, liquids, bonds, conductivity, and nearly every familiar material feature of the world involve electrons moving among positively charged nuclei according to quantum rules. Positrons do not settle into that same role. A positively charged particle with the mass of an electron cannot simply replace the electron in ordinary atomic structure and keep the world as it is. The electrical architecture would be wrong from the beginning. This is one reason the universe around us is not built from positrons. In the way it is built from electrons, electrons can be held by nuclei. Positrons cannot be held by ordinary nuclei in that same simple way because the charges do not invite one another together. Instead, a positron moving through matter is more like a visitor passing through a very crowded social gathering in which almost everyone has the wrong opinion about it. It is pushed away by nuclei and drawn toward electrons. That means its fate in matter is governed not by stable, long-term participation in atomic life, but by a sequence of interactions that usually ends in something much more dramatic. Before we get to that dramatic part, there's another important property to mention. The electron and positron also differ in what physicists call lepton number. This is one of those ideas that can sound technical, until you realise it functions almost like a conserved bookkeeping label. The electron carries one kind of assignment and the positron carries the opposite. This is not a decorative detail. It matters in particle reactions because nature is very strict about which combinations of particles can appear and disappear in a process. Charge must balance, energy and momentum must balance, and other conserved quantities must also work out. The electron and positron belong to opposite sides of this bookkeeping system, which is part of why they naturally come into discussions of pair creation and annihilation. They are not merely opposite in electricity, they are opposite in a deeper sense built into how particle identity is tracked. There is also the magnetic side of the story. Because both particles have spin and charge, they each have a magnetic moment. In very broad terms, this means they behave in magnetic fields as though they carry an intrinsic tiny magnet-like quality. The magnitudes match in the same way their masses and charge magnitudes do, but the orientation relative to charge is reversed. Again, the pattern is not one of loose similarity. It is one of almost perfect mirroring. The electron and positron are built into the theory as counterparts, and their measurable properties reflect that with extraordinary precision. All of this might leave you wondering whether the difference between them is really just a matter of sign conventions, the sort of thing humans could have chosen differently if the history of science had taken a different turn. That is a fair question, because words like positive and negative can sound arbitrary. We could indeed have named the electron's charge positive long ago and called the positron negative instead. The labels themselves are conventional, but the relation between the two is not. Whatever words we choose, one of them is opposite in charge to the other, opposite in lepton number, opposite in the role it plays in electromagnetic interactions. The labels are human. The symmetry is physical. An especially revealing way to understand the difference is to look at what happens when the two meet. An electron and a positron are drawn together by electric attraction. Since their masses are equal and their charges are opposite, they make a very natural pair. Under the right conditions, they can even form a short-lived bound state called positronium. This is one of the loveliest little systems in physics because it is in some ways like a stripped-down atom. Instead of a light electron orbiting a heavy proton, you have an electron and a positron bound together by their mutual electric attraction. Since the two have equal mass, the dance is more balanced. Each moves in response to the other. Positronium is unstable, but it offers a beautiful demonstration that the positron is not just a mathematical opposite. It is a genuine physical partner capable of forming a real quantum system with the electron. And yet that system does not last. Given the chance, the electron and positron annihilate. This word can sound more dramatic than the underlying physics requires, but the process is remarkable all the same. The pair disappears as particles, and their energy is carried away by radiation, usually in the form of gamma rays. This is not because one destroys the other in the way two solid objects might smash and shatter. It is because the particle and antiparticle are allowed by the rules of quantum field theory to convert their mass and motion into radiation, while preserving all the relevant conservation laws. Their opposite charges cancel. Their opposite lepton numbers cancel. The universe, in a sense, finds a more neutral way to store the same total energy. This is one of the clearest demonstrations that the difference between an electron and a positron is profound, even though it is encoded in a very compact set of properties. A tiny sign reversal is enough to make them mutual partners in disappearance. Ordinary particles in everyday matter do not usually vanish in such a clean way when they meet one another. The electron and positron do because they are linked at a deep level. The theory does not treat them as unrelated ingredients that happen to collide. It treats them as opposite excitations associated with the same underlying structure. That point leads us toward a modern way of speaking that is more powerful than the old image of particles as tiny independent pellets. In quantum field theory, the electron and positron are understood as corresponding excitations of the same underlying field. This is a subtle but important shift. Instead of thinking that there is one field for electrons and an entirely separate unrelated field for positrons, the theory tells us that the same field naturally includes both particle and antiparticle solutions. That is why the resemblance between them is so exact. They are not distant cousins. They are two faces of one deeper entity. This way of thinking also clarifies why the differences matter so much. If two excitations of the same field can carry opposite charge, then charge is not an afterthought painted onto a pre-existing object. It is part of the definition of the allowed excitation. The positron differs from the electron because the quantum state differs, not because the outer shell is painted in a different colour. At this level of physics, identity is inseparable from quantum numbers. What a particle is cannot be separated from what properties it carries. There is no hidden featureless bead underneath waiting to be described more plainly. The properties are the thing. That can take some getting used to because everyday language nudges us in the other direction. We like to imagine an object first and then its traits afterward. A ball may be red or blue, heavy or light. A chair may be wooden or metal. The object seems primary and the properties secondary. In particle physics, the distinction is harder to maintain. An electron is not a neutral little kernel that just happens to have electron-like properties attached. It is the set of properties and the rules of behavior taken together. The same goes for the positron. To ask what makes it different from an electron is to ask which fundamental quantum labels are reversed and what consequences flow from that reversal. Another useful contrast comes from how each behaves in ordinary environments. Electrons are abundant everywhere in matter. They are stable. They can sit in atoms indefinitely. They can move through conductors. They define chemistry and the structure of materials. Positrons, by contrast, are usually temporary in our everyday world. They can be created in certain radioactive decays, in high-energy collisions, in astrophysical processes, and in specialized equipment. But once they enter ordinary matter, they do not remain quietly embedded for long. They lose energy through interactions. They may briefly form positronium with an electron, and then they annihilate. So although the positron is every bit as real as the electron, it plays a very different practical role in the material world around us. That difference in role has a way of shaping intuition. Because electrons are everywhere and positrons are not, it is tempting to think of the electron as the normal particle and the positron as an exceptional variation. But the laws of physics do not really see it that way. The asymmetry is environmental, not fundamental. Our world contains a great surplus of matter over antimatter, so electrons have a place to persist while positrons usually meet electrons and disappear. In a different cosmic setting, one can imagine a world in which positrons were plentiful and electrons rare, and the emotional sense of which particle is ordinary would flip along with the circumstance. Physics is very good at reminding us that familiar is not the same as fundamental. There is an even subtler point worth noticing. The electron and positron are opposite in charge, but they are not different in the way an electron and a proton are different. The electron and proton differ in mass by a large amount. They also belong to different families in the modern particle classification. The proton is not elementary in the same sense. It is made of quarks bound by the strong interaction. The positron does not differ from the electron in that way at all. Its difference is cleaner and more exact. Same mass, same spin, opposite charge, opposite lepton number, same status as an elementary particle, at least within our present best theory. This is why the phrase mirror electron is so useful. It captures something that comparisons with other positive particles do not. The precision of that mirror relationship has been tested in many ways. Physicists compare the properties of particles and antiparticles with extreme care because any tiny mismatch beyond what the theory permits could point to new physics. So far, the electron and positron agree to astonishing precision wherever the established theory says they should. This is one of the triumphs of modern physics. The symmetry is not a loose poetic idea. It is quantitative. The universe seems committed to it at a very deep level. Still, even here, one must be careful not to become too casual. Saying that the positron is just an electron with positive charge can be useful as a first sentence, but it can also hide the depth of the concept if left unexamined. The positron is not an electron that changed its mind. It is not an electron turned inside out. It is not a positive version assembled from the same little pieces with a sign swapped by hand. It is the electron's antiparticle, defined through the structure of the theory and confirmed through experiment. The distinction lies in fundamental quantum identity, not in personality or circumstance. There is also something worth appreciating about how little nature needs in order to create large effects. A reversal of charge and associated quantum number is enough to alter the entire fate of a particle in matter. The electron becomes a stable participant in atoms and chemistry. The positron becomes a transient visitor that seeks out an electron and vanishes with it. Same mass, same spin, nearly the same mathematical treatment, completely different everyday destiny. It is a reminder that in physics the world is often shaped less by bulk differences than by rule-based ones. Tiny changes in allowed interactions can produce enormous differences in outcome. And that naturally brings the mind back to the deeper question. If the positron and electron are so alike in measurable structure, yet so different in role and interaction, then what exactly are we dealing with when we call either one a particle? Are they tiny objects with hidden interiors? Are they truly fundamental? Are they made of anything at all in the ordinary sense? That is where the discussion has been quietly heading all along, because once we understand that the difference between electron and positron is not a matter of size or visible composition, but of quantum identity, the old everyday idea of what something is made of starts to feel a little too blunt for the job. That question sounds so simple that it almost feels rude to answer it with anything complicated. Is a positron made of anything at all? In everyday life, that is exactly the kind of question that works beautifully. If you ask what bread is made of, you get flour, water, yeast, and salt. If you ask what a table is made of, you get wood, metal, glue, and perhaps a regrettable amount of flat-pack optimism. If you ask what a planet is made of, you get rock, metal, gas, ice, and many years of cosmic untidiness. We are used to a world in which objects are built from smaller objects, and those smaller objects can often be taken apart again. So the question arrives with a kind of common sense attached to it. Surely a positron must also be made of something. Surely there is some deeper layer, some hidden stuffing, some tiny inner arrangement, and this is where modern physics becomes both very precise and slightly uncooperative. The best answer we currently have is that a positron does not appear to be made of smaller parts in the way a molecule is made of atoms, or a proton is made of quarks. As far as all present evidence goes, it behaves like an elementary particle. That word elementary is doing a great deal of work. It does not mean childish or simple in the everyday sense. It means that when we probe the positron, as deeply as we know how, we do not find signs of internal structure. We do not see pieces inside it. We do not detect a size in the ordinary mechanical sense. We do not catch it breaking into subcomponents the way a composite object would. Within the framework of our best current theory, the positron is not assembled out of smaller building blocks. It is one of the building blocks. Now that sounds like a very strong claim, and it is. But physics is careful about such things. It does not say this with divine certainty or theatrical finality. It says it the way a good investigator speaks after very careful testing. We have looked hard. We have found no evidence of internal pieces. Our most successful theory treats the positron as fundamental. If there is something deeper still, it has not yet shown itself in any experiment. So the honest answer is both firm and modest. The positron is elementary according to everything we presently know. Still, that answer can feel strangely unsatisfying when first heard. Not because it is weak, but because it clashes with the habits of ordinary thought. We are trained by life to expect smaller parts underneath larger things. A wall is made of bricks. A brick is made of grains. A grain can be traced to molecules and crystal structure. The whole world seems happy to cooperate with the idea that to understand something fully is to take it apart. We become little detectives of nested structure. Open the box, then open the smaller box inside it, then the smaller one still. But modern particle physics forces us to consider the possibility that the boxes do not continue forever in the same style. To see why this is so unsettling, it helps to compare the positron with something that genuinely is made of smaller ingredients. Take the proton. For a long time, the proton looked elementary too. It sat inside the atomic nucleus and seemed, from a certain distance, like a basic unit of matter. But as experiments became more powerful, physicists discovered that the proton is composite. It contains quarks bound together by gluons. It has internal structure. If you scatter very energetic particles off a proton, The results reveal that it is not a featureless point. There is something inside to hit. The proton has a complicated interior life, which is more than many people can say before their morning tea. The positron does not behave that way. When it is probed in high-energy experiments, it keeps acting like a point-like particle. That does not mean it is literally a tiny little bead with a perfect hard surface and no thickness. It means that within the resolution of the experiment there is no sign of substructure. The positron does not present an internal arrangement the way the proton does. It behaves as though it has no smaller pieces waiting to be discovered by that particular method. This is why the distinction between composite and elementary matters so much. It is not philosophical decoration. It shows up in real measurements. There is another source of confusion hidden in the phrase made of. In everyday speech, to be made of something usually means to be built from smaller chunks of stuff. But at the deepest levels of physics, that notion may no longer be the right one. The question is not foolish. It is exactly the right question to ask. But the answer may require updating the meaning of made of itself. A positron may not be made of smaller objects. Instead, it may be a basic excitation of an underlying field. That sentence can sound alarmingly technical if introduced too quickly, but it is really the heart of the modern answer. In the current picture of particle physics, the universe is not best described as empty space sprinkled with tiny solid pellets. It is better described as a set of fields that fill space. Each type of particle is associated with a field. The electron and the positron are linked to the same deeper field. What we call a particle is, in this view, a localized quantum excitation of that field. This is a more subtle idea than the old picture of miniature billiard balls. It says that the particle is not a little object sitting inside the field the way a raisin might sit inside a bun. The particle is the field doing a particular kind of thing. An everyday analogy can help so long as we do not trust it too far. Think of the surface of a pond. If the water is calm and then a ripple travels across it, you do not ask what the ripple is made of in quite the same way you would ask what a pebble is made of. The ripple is not a separate object built from hidden ripple bricks. It is a pattern in the water. The water is the deeper medium, and the ripple is one possible state of motion within it. Now, a positron is not literally a pond ripple, and space is not a watery surface, so we should not become too attached to the image. But it helps make one crucial point. Some real things are patterns or excitations rather than little assembled lumps. Their reality is not weakened by that. It is simply a different kind of reality. This is where the question becomes more interesting, not less. If the positron is not made of smaller parts, then what exactly is it? The modern answer is that it is an elementary excitation of the electron field, with properties opposite to those of the electron in the relevant ways. Same mass, same spin, opposite charge, opposite lepton number, not a positive electron in the casual sense, but the electron antiparticle arising naturally from the structure of the field itself. Once you adopt that picture, the positron stops looking like an inexplicable duplicate and starts looking like a necessary feature of the theory. There is an important warning to insert here because popular explanations sometimes wander off into confusion. People often hear that particles can be created from energy and then conclude that a positron is made of energy. That sounds reasonable at first, but it is not quite the right way to say it. Energy is not a kind of material stuffing from which particles are moulded like pastries from dough. Energy is a property, a quantity, something systems possess and exchange. When enough energy is concentrated in the right way, a particle and antiparticle pair can be created. But that does not mean the resulting positron is made of energy in the same everyday sense that bread is made of flour. It means the laws of physics allow energy to appear in the form of particles. The distinction matters. Otherwise, energy starts sounding like a magical substance poured into every gap in our understanding, and physics has enough work to do already without turning energy into soup. The same sort of care is needed with the word point-like. When physicists say the positron appears point-like, They are not claiming to have photographed a tiny dot with perfectly sharp edges. They mean that experiments have not revealed any measurable size or internal structure. In the equations, it is treated as elementary. In the data, it behaves accordingly. Point-like is a statement about structure and behaviour, not a statement that the positron is literally a miniature grain of cosmic sand. One of the reasons this takes time to absorb is that common sense keeps trying to sneak back in through the side door. We imagine that if something is real, it must be an object in the old mechanical sense. It must have a little inside and a little outside. It must be composed of something more basic, even if only unimaginably small. But quantum field theory teaches a different lesson. At the deepest level currently known, the universe may not be built out of tiny solid objects at all. It may be built out of fields, and the particles may be the stable excitations those fields support. In that case, asking what a positron is made of is a little like asking what a note from a violin is made of. The note is real, it can be measured, it has a frequency, it carries energy. It affects the world, but it is not assembled from smaller note fragments. It is a pattern produced by a system that can sustain it. Again, no analogy should be trusted all the way to the bottom. A note in the air is not a quantum particle, but the analogy helps loosen the old expectation that every real thing must be a tiny container full of tinier things. Sometimes reality is more like structure than stuffing. Now, there is a fair objection one might raise at this point. Has physics not done this before? Has it not called things fundamental and then later discovered deeper layers? Yes, absolutely. Atoms were once thought indivisible, then they were found to contain nuclei and electrons. Protons and neutrons were once treated as fundamental in a similar way. Then came quarks. Physics has been humbled often enough that it should never become smug. So when we say the positron is elementary, we do not mean that no deeper theory could ever replace the present one. We mean that within all tested experiments so far, the positron behaves as an elementary particle, and our best theory treats it that way with extraordinary success. That is the right scientific posture. Confident but not arrogant. Clear but not final in a theatrical sense. If some future theory reveals that what we call the positron emerges from a deeper framework, then physics will update accordingly. But it would have to explain why the present description works so remarkably well. A new theory cannot simply be different. It must be better and still account for what has already been measured. Until that day, if it ever comes, the positron stands as one of the basic known ingredients of nature. Another way to approach the question is to ask what kind of evidence would count as proof that the positron is made of smaller parts. If it were composite, we might expect to see excited internal states, a kind of internal vibration or rearrangement that reveals substructure. We might expect scattering experiments to show departures from point-like behaviour. We might detect a size. We might observe processes hinting that the positron can break apart into more basic components under suitable conditions. None of that has been seen. Instead, every test continues to support the idea that the positron has no internal architecture of the familiar sort. This makes it very different from the proton, and comparing the two is useful because it prevents the discussion from drifting into pure philosophy. These are not just words. Composite particles and elementary particles behave differently in experiments. The proton has measurable structure, the positron does not. That is not a matter of taste or mood, it is a matter of data. There is also something deeply satisfying about the way the positron fits into the modern framework. If it were just a random particle added by hand, the theory would feel untidy, but it is not random. The positron appears naturally once the theory is built correctly. It is the antiparticle partner demanded by the structure of the relativistic quantum description of the electron field. In that sense, the positron is not a decorative extra. It is part of the architecture. The laws do not reluctantly allow it. They seem to require it. That point matters because it changes how we think about explanation. The old style of explanation says this thing exists because it is built from these smaller parts. The newer style, at least at this level, says this thing exists because it is an allowed excitation of a field with certain symmetries and conservation laws. That may feel less tangible at first, but it is not less explanatory. It is simply a different kind of explanation. Instead of hidden gears, you get deep structure. Instead of stuffing, you get rules and permitted states. Some people find that disappointing. They want the world to end in a pile of tiny pebbles. Others find it thrilling because it suggests that reality is more elegant than a mere heap of parts. I suspect most of us feel both reactions at different times, depending on the hour and how much sleep we have had. The desire for little pieces is very human. It promises a solid finish line. But the field picture offers something else, a universe in which what is basic may not be stuff in the old sense, but lawful patterns that can appear, interact, and disappear according to astonishingly precise rules. The positron is one of the clearest examples of this shift in thinking, because it looks at first like the kind of thing that ought to be built from smaller ingredients. It has mass. It can move. It can be created and annihilated. It leaves tracks in detectors. It sounds like an object, but the deeper we look, the more it resists being treated as a tiny machine with components. It behaves instead like something elementary, something whose identity is bound up with its quantum properties and the field from which it arises. This also helps explain why the positron and the electron can annihilate. If you cling too tightly to the old image of each as a tiny bead of substance, annihilation sounds impossible or at least suspicious. Where does the stuff go? But if particles are excitations of fields, and if the theory allows those excitations to convert into radiation, while preserving all the relevant quantities, then the process makes much more sense. The electron and positron are not indestructible little pebbles colliding. They are quantum states that can transform. The reality is still perfectly physical and measurable, but it is more dynamic than the old substance picture suggests. There is a broader lesson hiding here. Sometimes the hardest part of learning physics is not memorizing strange facts. It is giving up the wrong kind of familiarity. We want the universe to remain understandable in terms borrowed from chairs, pebbles, and machinery. And for much of ordinary life, those terms work beautifully. But when we descend to the level of fundamental particles, the old language starts to bend. Not because the world becomes unreal, but because it becomes more basic than the habits of daily thought. So, is a positron made of anything at all? If by made of you mean built from smaller constituent particles, in the way atoms are built into molecules or quarks into protons, then the best answer is no, not as far as we know. If by made of you mean does it arise from something deeper than itself, then yes, in the modern picture it arises as an excitation of an underlying field. And if by made of you mean is it some condensed form of energy, then only with care, because energy is not a substance, but a property that can take particle form under the right conditions. What makes the question especially rich is that it forces us to refine our intuition. We begin by imagining a positron as a tiny object and asking what is inside it. We end by discovering that inside may not be the right category at all. The more appropriate question becomes what deeper structure allows this particle to exist, and why does that structure produce both the electron and the positron as natural possibilities? That is the step from old atomic thinking to modern field thinking, and it is one of the great conceptual moves in physics. It is also where the story becomes even more interesting, because once we stop imagining the positron as a miniature positive pellet, and start thinking in terms of fields, the whole landscape changes. The particle is no longer the starting point. The field is. And from that field come the particles, their antiparticles, their interactions, and the strange but orderly processes by which matter and antimatter can appear and disappear. That is the point where the question of what the positron is made of starts giving way to a better one. Namely, what sort of world must this be if something as specific and exact as a positron can emerge from a field in the first place? Once we let go of the idea that the positron must be a tiny object with smaller pieces inside it, the next step is not to throw up our hands and say that physics has become vague. In fact, the opposite happens. The description becomes more exact. It becomes less intuitive at first, but more powerful. And that shift matters because the old image of particles as tiny hard balls moving through empty space is one of those ideas that feels obvious only because it resembles everyday experience. We live among chairs and stones and raindrops and bits of dust. We are surrounded by objects that seem to have edges, surfaces, and little volumes of matter inside them. So when we hear the word particle, we instinctively shrink that familiar picture down to an absurdly small scale. We imagine something like a microscopic bead, perhaps far too tiny to see, but still bead-like in essence. Something with a location, a path, and a little compact self. That picture is useful right up to the moment it stops being useful, which in modern physics is rather early. The trouble is not merely that particles are too small for us to picture clearly. The trouble is that at the quantum level they do not behave like tiny classical objects. If they did, the world would be much easier to explain and much less interesting. But they do not. They interfere. They appear and disappear in ways that ordinary objects do not. They can be created and destroyed in interactions. Identical particles are genuinely indistinguishable in a way that goes far beyond two identical marbles from the same factory. And when we try to combine the quantum description of nature with relativity, the old little ball picture begins to fall apart even more decisively. It simply is not flexible enough to describe what experiments actually show. This is why the modern picture turns from particles as objects to fields as the deeper reality. That can sound abstract when stated too quickly, but it becomes clearer if we take it one step at a time. A field in physics is something defined throughout space. The temperature in a room can be described as a field because at every point there is some value for how warm it is. The same goes for the air pressure in the atmosphere. You do not have tiny pressure balls flying around. You have a value spread across space, changing from place to place. A field is not an object sitting in space. It is something that exists through space. Long before quantum field theory arrived, physics already knew about fields. Electricity and magnetism were described this way. Instead of imagining forces reaching invisibly from one object to another with no medium in between, physicists learned to think in terms of electric and magnetic fields filling the region around charges and currents. That was already a major conceptual advance. It replaced one kind of mystery with a much more structured description. The field became part of the physical world, not just a bookkeeping device. Quantum field theory pushes that idea much further. It says that the basic ingredients of the universe are fields, and what we call particles are quantized excitations of those fields. That phrase can sound heavy, but the core idea is surprisingly simple once you sit with it. A field can be quiet or excited. Under the right conditions, it can support a localized packet of energy and momentum that behaves like a particle. The particle is not a tiny pellet hiding inside the field. It is the field in a particular excited state. This is a dramatic shift in viewpoint, and it takes time to feel natural. We are so used to asking what a thing is made of that it feels almost unsporting when physics answers by changing what kind of thing it thinks a particle is. But once you make that shift, many features of the positron become easier to understand. The positron is not best imagined as a miniature positive ball. It is an excitation of the same underlying field associated with the electron. The electron and positron are not two separate little bits of stuff that happen to resemble one another. They are two allowed excitations with opposite charges and related quantum properties arising from a deeper field structure. An analogy may help, provided we keep it on a short leash. Think of a guitar string. The string can sit quietly or it can vibrate. Different patterns of vibration are possible. Those patterns are real, measurable, and they carry energy. The note you hear is not a tiny object hidden inside the string waiting to leap out. It is the string behaving in a certain way. Now, the universe is not literally a room full of guitar strings, and particles are not little notes in the simple musical sense. But the analogy captures something important. A pattern in a system can be every bit as real as an object. and sometimes more fundamental to the description. The field is like the deeper system. The particle is like one of the allowed excitations. Another comparison people often use is a ripple on water. Again, not because the universe is secretly a pond, but because a ripple is clearly real without being a separate chunk of material. You can measure its speed. You can see it carry energy. It can interact with other ripples. Yet you would not ask what the ripple is made of in the same way you would ask what a pebble is made of. The ripple is a state of the water. In something like that spirit, the positron is a state of the field. Where this becomes especially valuable is in dealing with creation and destruction. In the old little ball picture, it is hard to explain how particles can simply appear in one process and vanish in another without sounding as though matter has become unreliable. But if particles are excitations of fields, then creation and annihilation are no longer so conceptually shocking. An interaction can supply enough energy for a field to become excited in a way that produces a particle and its antiparticle. Later, those excitations can interact and transfer their energy into another field, such as the electromagnetic field, producing radiation instead. Nothing mystical has happened. The fields are still there. What changes are the excitations present in them? This is one reason quantum field theory became the language of modern particle physics. Ordinary quantum mechanics, in its earlier form, was good at describing systems with a fixed number of particles such as electrons bound in atoms. But when experiments began involving processes where particles could be created and destroyed, something more flexible was needed. A theory built on fields could handle that naturally. A field can have no excitations, one excitation, many excitations. It can exchange energy with other fields. It can produce the rich set of processes actually observed in nature. For the positron, this is not a side issue. It is central. The positron was not fully understandable in the old mechanical style. Its existence makes better sense in a theory where electron and positron arise together from a relativistic quantum field. Once the field is quantized properly, both particle and antiparticle appear as part of the structure. That is why the positron feels so exact in its relationship to the electron. Same mass, same spin, opposite charge. This is not a lucky coincidence. It is built into the field description from the beginning. There is also a practical reason physicists prefer the field picture. Experiments demand it. If electrons and positrons were really just tiny classical objects, they would not produce the interference patterns that real quantum particles do under the right conditions. They would not obey the deep rules of indistinguishability in the same way. They would not fit naturally into a relativistic theory where antiparticles arise and particle number can change. The little ball image is not just incomplete, it actively becomes misleading. It encourages the wrong questions and makes the right answers sound stranger than they actually are. One of the hardest things to accept is that a particle in quantum field theory is not an object in the ordinary sense, but it is also not a mere blur of ignorance. It is not that we simply do not know where the little ball really is. The theory is telling us something stronger. The particle is a quantized excitation with specific properties and probabilities attached to how it behaves in measurements. Before an interaction or detection, it is not quietly behaving like a classical bead behind our backs. This is where classical intuition objects most loudly, because we want the world to keep its old furniture, even when the experiments have already removed it. The positron is a good guide here because it forces the issue cleanly. If you try to imagine it as a tiny positively charged sphere travelling along a crisp path through a vacuum, you will quickly run into trouble when you ask how it is produced, how it annihilates with an electron, or why it must be treated as the antiparticle partner arising from the same field. But if you think of it as an excitation of a field, much of the mystery moves from what kind of object it is to what kind of field structure allows it. That is progress. Physics is not making the problem disappear, it is relocating it to the right level. This also helps explain why the vacuum in modern physics is not simply empty nothingness. In classical thinking, empty space is just a blank stage on which objects move. In quantum field theory, The vacuum is the lowest energy state of the fields. It is not a box with nothing inside. It is the ground state of a set of fields that exist everywhere. Under the right conditions, those fields can be excited. Particles can emerge. So even empty space is not quite as empty as common sense would like. It is structured, though quietly so. That structure matters because it is the background from which particles like positrons can arise. There is a mild irony in all this. The field picture sounds more abstract than the particle picture, but it is actually closer to what the mathematics and experiments demand. The tiny ball picture sounds concrete, yet it is often the more naive one. Physics has a habit of doing that. It makes us trade a simple image for a more accurate framework, and the trade often feels like a loss until the new framework starts to reveal how much more it can explain. For example, once you think in terms of fields, the existence of antiparticles becomes much less shocking. If the field is quantized in a relativistic way, the theory naturally includes excitations corresponding to both particles and antiparticles. That was part of the deep lesson of the positron. It was not just an unexpected oddity glued onto the edge of electron theory. It was a sign that the field description was the right kind of language. A theory built correctly did not merely tolerate the positron, it required it. This is also why asking where the positron is made can become the wrong kind of question if one is not careful. It assumes that the positron is a thing with an inside, like a watch or a seed. But the quantum field picture says that the more appropriate question is what field state the positron is, what properties define it, how it interacts, and how those interactions can change the pattern of excitations present. The shift is from composition to structure, from stuffing to state. That may sound less satisfying at first because it denies us the pleasure of opening one more box. But in exchange, it gives something richer. It shows that the universe may be organized less like a pile of tiny parts and more like a system of fields with allowed excitations, strict symmetries, and interaction rules that can be tested with astonishing precision. The positron is not less real because it is a field excitation. If anything, it is more deeply placed in the theory. It belongs to the architecture, not just the inventory. There is another subtle benefit to the field picture. It explains why all electrons are identical, and likewise why all positrons are identical. In everyday manufacturing, no two objects are ever truly perfect copies. One grain of dust differs from another. Two chairs made on the same day by the same machine will still have tiny distinctions. But all electrons are the same in the deepest measurable sense. They do not come in slightly different models with better finish or improved suspension. The same goes for positrons. That exact sameness is much easier to understand if each one is an excitation of the same field. They are not individually crafted items. They are repeated instances of one kind of excitation. The field guarantees the identity. Now, one should not push the picture into oversimplification. A field is not just a smooth classical medium quietly wobbling like a sheet in the wind. Quantum fields are governed by rules that are more subtle than any ordinary substance we know. Their excitations are quantized. Their interactions involve probabilities. The vacuum state itself has structure. So while analogies with strings and ripples and notes are helpful, they are only entry points. The real theory is more exact and less visual than any analogy can manage. Still, for a calm understanding of the positron, the central move is enough. Stop picturing it as a tiny positive bead. Start picturing it as a quantum excitation of a field. Then notice how much begins to make sense. Its relation to the electron becomes exact rather than mysterious. Its creation from energetic processes becomes understandable. Its annihilation with an electron becomes a lawful transformation rather than a magical disappearance. Its elementary nature becomes easier to accept because one is no longer searching for miniature gears hidden inside it. This shift also changes how we think about matter itself. If electrons are field excitations, and positrons are field excitations, and photons are field excitations, then the basic content of the world is no longer a collection of little pellets scattered in emptiness. The world becomes a web of fields, with particles as the localized events we detect when those fields are excited in certain ways. That is a much stranger picture than the classical one, but it is also far more coherent once you see what it is trying to do. And it leaves us in an interesting place. We started by asking what the positron is really made of. We found that the best modern answer is not smaller balls inside bigger balls, but fields supporting quantized excitations. Now another question begins to rise quite naturally. If the positron is an excitation rather than a tiny built object, how exactly can such an excitation come into existence? Under what conditions does the universe produce one? What does it mean for energy to take the form of a positron and an electron together? That is the next step in the story, because once the field picture is in place, the appearance of particles from energy is no longer a bizarre exception. It becomes one of the most direct demonstrations that the world at its deepest level is organized by fields and the excitations they permit. One of the strangest consequences of the field picture is that it changes what we mean by appearance. In ordinary life, when something appears, we usually assume it must have come from somewhere in the familiar sense. A coin appears on the table because someone placed it there. A loaf of bread appears because someone baked it. Even when something seems sudden, we still expect a chain of ordinary events leading up to it. But at the level of particle physics, appearance does not always mean that some tiny object was hiding nearby and then wandered into view. Sometimes it means that under the right conditions, enough energy has been concentrated in the right way for a field to become excited and produce new particles. That is not a poetic description or a loose metaphor. It is one of the basic operating principles of the quantum world. This is where the positron becomes especially revealing. Because it is the antiparticle partner of the electron, it often arrives in processes that show, with unusual clarity, how the universe can convert energy into matter and antimatter together. If you wanted a single example that forces the mind to give up the old image of reality as a pile of tiny permanent pellets, the appearance of a positron from light would be an excellent choice. It is real, measurable, and surprisingly direct. Under suitable conditions, a photon of sufficiently high energy can give rise to an electron and a positron. Light, in other words, can become matter and antimatter. That sentence deserves to be handled with some care, because it is easy to say it too casually and leave behind the impression that particles simply pop out of nowhere in a sloppy or magical way. They do not. Nature is much stricter than that. Every such process must obey the conservation laws that physics takes very seriously. Energy must be conserved. Momentum must be conserved. Electric charge must be conserved. Other quantum quantities must also balance properly. When a positron appears, it does so within a process that respects all of these rules with ruthless precision. The result looks dramatic, but the bookkeeping is immaculate. To understand how this works, it helps to start with the photon. A photon is the quantum of the electromagnetic field, the particle associated with light. Now, in daily experience, light does not feel especially heavy or matter-like. It shines, warms, illuminates, and occasionally reveals just how dusty a room really is. It does not look like the sort of thing that ought to become an electron and a positron. But that instinct comes from the soft, low-energy light we live with most of the time. Sunlight, lamplight, the glow from a screen, all of that belongs to a range that is far too gentle for the job. If the photon is energetic enough, however, the situation changes completely. At very high energies, a photon is no longer just a harmless little messenger of illumination. It becomes capable of participating in processes that can create particles. If the conditions are right and the energy is sufficient, the photon can produce an electron and a positron as a pair. This is often called pair production, and the name is wonderfully plain for such a strange event. The pair appears together because the conservation laws demand it. The positron carries positive charge, the electron carries negative charge, and the total charge remains balanced at zero, just as it was for the original photon. The energy of the photon is transformed into the mass and motion of the new particles. This is one of the most famous demonstrations of the deep link between energy and mass in modern physics. Mass is not a separate, untouchable ingredient that must always have existed beforehand in the form of little chunks. Under the right circumstances, energy can take particle form. But here, once again, the details matter. A photon cannot simply drift through empty space and, all by itself, turn into an electron and a positron. That would seem like the simplest version of the story, but nature does not allow it in that straightforward form. The problem is not energy alone, the problem is momentum as well. A single photon carries energy and momentum in a linked way. If it were alone in empty space and attempted to become an electron and a positron, there would be no way to satisfy all the conservation rules at once. Something else must be involved to help balance the process. In practice, pair production usually occurs near an atomic nucleus, or in the presence of another particle or another photon. The nearby participant helps absorb or balance momentum so that the transformation can actually happen. This is one of those places where physics is more disciplined than first impressions suggest. The process is not forbidden because nature is being difficult. It is forbidden because the arithmetic of reality has to close properly. The version most often described in introductory discussions is a high-energy photon passing near the nucleus of an atom. The photon enters the strong electric field around the nucleus, and if it has enough energy, it can produce an electron and a positron. The nucleus is not there to donate a secret stash of matter, as though it were lending out spare parts from a cupboard. Its role is mainly to help with momentum conservation. It recoils slightly, taking up the necessary balance so that the process can occur consistently. The photon provides the energy. The fields and the conservation laws determine whether the transformation is allowed. It is worth pausing on that, because it is easy to imagine the nucleus as the true source of the new particles, but that is not the right picture. The nucleus is more like a participant that makes the reaction possible. The energy budget still comes from the photon. If the photon does not carry enough energy, nothing happens. It may scatter, it may pass on, but it will not produce the pair. There is a minimum threshold. The photon must carry at least enough energy to account for the mass of both the electron and the positron, and in practice, it must usually carry a bit more, because the created particles may move away with some kinetic energy, and the nucleus may recoil slightly as well. This threshold point is important, because it reminds us that mass is not free. A positron cannot be created on a budget of wishful thinking. Nature requires enough energy to account for what appears. If an electron and positron come into existence, their masses must be paid for, so to speak, along with whatever motion they carry afterward. That is why ordinary visible light does not go around producing matter in your living room. Its photons are nowhere near energetic enough. You need gamma rays or similarly extreme conditions, the kind more often found in high-energy environments, radioactive processes, cosmic events, or specialized laboratory setups than beside a bedside lamp. The phrase from energy and light can therefore be taken quite literally, but not casually. Yes, a positron can arise from light, but only from light energetic enough to do the job, and only in a context where the conservation laws can all be satisfied. Once those conditions are met, the process is not rare in principle. In fact, it becomes one of the standard ways positrons are produced in high-energy physics and in certain natural environments. There is another version of pair production that is even cleaner conceptually, though often less intuitive at first. Instead of one photon interacting near a nucleus, two photons can collide with enough combined energy to produce an electron and a positron. This is sometimes discussed in more advanced settings because it shows very plainly that the electromagnetic field can generate matter and antimatter under the right conditions. Here again, nothing mystical is happening. The photons bring in the energy and momentum, and the outgoing electron and positron carry them away in a new form. But the conditions must be quite extreme. Photons do not often collide with sufficient energy in ordinary settings. When they do, however, the universe shows no reluctance at all about converting radiant energy into particle pairs. This is one reason the early universe must have been a very lively place. In the beginning, when temperatures were unimaginably high and radiation energies immense, photons were energetic enough to create particle-antiparticle pairs all the time. Electrons and positrons would appear and disappear constantly, produced from energetic radiation, and then annihilating back into photons again. The young universe was not a calm place full of settled objects. It was a hot, dense, rapidly interacting environment in which matter and radiation traded forms almost continuously. The positron belongs very naturally to that world. In some sense, it is one of the signatures of a universe where energy is high enough for fields to express more of their possibilities. If that sounds dramatic, it should, but there is also something oddly practical about it. The same underlying physics appears not only in cosmic settings, but in laboratories and technology. Positrons are not just theoretical decorations from the early universe. They can be produced in radioactive decays, in collisions of energetic particles, and in medical imaging techniques that rely on their annihilation. The idea that energy can produce a positron is not a speculative flourish. It is part of the working machinery of modern science. At this point, it is worth distinguishing pair production from another important source of positrons, because otherwise the story can become too narrow. Positrons do not only come from photons turning directly into electron-positron pairs. They can also appear in a type of radioactive decay known as beta-plus decay. In that process, a proton inside an unstable nucleus transforms into a neutron while emitting a positron and a neutrino. That route is not simply a photon becoming matter. It involves the weak interaction, one of the other fundamental interactions in nature. The reason to mention it here is that it shows the positron is not tied to one single birth mechanism. Nature can produce it in several ways depending on the circumstances and the interaction involved. Still, pair production from high-energy light remains especially important because it displays the deeper principle so directly. Light can become matter and antimatter together. That is the line that changes how one thinks about particles. It breaks the old habit of imagining matter as something permanently separate from radiation. In the quantum field picture, those categories are linked. Excitations of one field can, through interaction, give rise to excitations of another. Fields talk to one another, so to speak. A photon is an excitation of the electromagnetic field. An electron or positron is an excitation of the electron field. Under the right conditions, the interaction between these fields can reassign the energy from one form to another. This is also a good moment to clear away a very common misunderstanding. People often hear that a photon can become an electron and a positron, and imagine the photon as a tiny ball that somehow splits in half, with one half becoming the electron and the other half becoming the positron. That is not the right picture. The photon is not a little lump being chopped into two smaller lumps, nor is the positron somehow hidden inside the photon waiting for release like a toy in a holiday cracker. The process is better thought of as a transformation allowed by the interacting fields. The incoming state contains a photon and perhaps a nucleus or another photon. The outgoing state contains an electron and a positron, with all the required balances preserved. The language of splitting is tempting, but it belongs too much to the world of ordinary objects. Another thing that deserves attention is timing. At the human level, we're used to cause and effect unfolding in a comfortably stretched sequence. First this happens, then that happens, then we react with either admiration or paperwork. In particle processes, the sequence can be so rapid that asking which exact instant the positron became real is not always the most fruitful question. The better question is whether the initial conditions and interactions permit the transition from one set of particles to another. The mathematics describes amplitudes for processes, probabilities for outcomes, and conservation rules. Reality then presents the result in the detector. The positron appears not by squeezing through a tiny door in time, but because the quantum process as a whole allows it. This style of description can feel less mechanical than people expect, but it is actually more faithful to what experiments show. When high-energy photons pass through matter, detectors reveal tracks consistent with electron-positron pair production. The two particles emerge, curve in opposite directions in a magnetic field because of their opposite charges, and can be measured. The event is not guessed at. It is recorded. It leaves evidence. This is one of the recurring comforts of particle physics. However strange the theory becomes, it keeps returning to concrete traces in real instruments. There is also something deeply balanced about the way the positron appears. It almost never arrives alone from light. It comes with an electron partner. That is not merely a convenience. It is part of how the world keeps its books straight. A photon begins with no electric charge. If it is to generate charged particles, the total must still add up properly. So the universe creates a positive and a negative together. One could say, without being too sentimental about it, that the positron enters the scene in company. It is born with its opposite, linked from the start by the very rules that permit its existence. This pairing has major consequences later, because once both particles exist, they can move apart, lose energy, interact with surrounding matter, or in some cases find one another again. If they do meet under the right conditions, their story can reverse direction. The electron and positron can annihilate, giving their energy back to light in the form of gamma rays. There is a pleasing symmetry in that. Light can become an electron and a positron, and an electron and positron can become light again. The fields permit both directions, provided the circumstances and conservation laws cooperate. Matter and radiation are not separate kingdoms with sealed borders. They are connected regions within the same deeper physical order. That two-way traffic is one of the great conceptual achievements of modern physics. It tells us that particles are not eternal pebbles moving through a passive void. They are states that can arise and transform. The positron is especially useful in teaching this lesson because its very existence is tied to such transformations. It is not a background resident of ordinary matter in the way electrons are. It more often appears in energetic events, travels a while, and then meets a fate determined by the material environment around it. That gives the positron a kind of narrative clarity. Its life story is often compact enough that the underlying principles stand out sharply. In ordinary matter, a newly produced positron does not usually enjoy a long independent career. As it moves through a material, it interacts with electrons and nuclei, losing energy along the way. Because it has positive charge, it is repelled by nuclei and attracted to electrons. Eventually, when it slows enough, it may briefly form positronium with an electron, or it may annihilate more directly. The details depend on the environment, but the general pattern is clear. Its birth may come from energy and light, but its future is usually tied to matter, and especially to the electron waiting somewhere nearby. That makes the creation of positrons from light feel less like a standalone trick, and more like the opening of a sequence. First, the energy is concentrated enough for the pair to exist. Then the pair enters the world of interactions. Then each particle follows the consequences of its charge, mass, and surroundings. The positron is never just a detached curiosity. Once created, it behaves according to very specific rules, and those rules are what make it detectable, usable, and scientifically revealing. What I find especially satisfying about this whole picture is that it shows how modern physics answers a very old human wish. We have always wanted to know how the world changes form, how one thing becomes another, how light, matter, heat, motion, and structure are connected. The appearance of positrons from energy and light is one of the cleanest answers nature offers, not because it is easy to imagine, but because it is so tightly governed. The transformation is not vague. It is exact, and that exactness is what makes it beautiful. So when we say that a positron can appear from energy and light, we are really saying several things at once. We are saying that the fields underlying nature can exchange excitation in lawful ways. We are saying that energy can take the form of particle mass when conditions allow. We are saying that light at high enough energy can produce matter and antimatter together. and we're saying that the positron is not a permanent hidden pellet waiting in the dark, but a real quantum excitation that the universe can create whenever the rules are satisfied. From here, the next step follows almost automatically. Once the positron has appeared and entered ordinary matter, it does not remain untouched for long. Its positive charge draws it toward electrons, and the symmetry that allowed the pair to be created from light also allows the reverse process to occur. That is where the story becomes even more striking, because the meeting of matter and antimatter is not just another collision. It is one of the clearest demonstrations that particles can vanish as particles while their energy lives on, and the positron, having emerged from energy in the first place, seems almost designed to teach that lesson. There is something about the word annihilation that makes people sit up a little straighter. It sounds final, severe, and perhaps slightly theatrical, as if physics has briefly borrowed the vocabulary of myth. And to be fair, the process itself is dramatic enough to deserve some attention. When a positron meets an electron, the two can disappear as particles and give their energy back to radiation. Matter and antimatter meet, and what remains is not a pile of wreckage or a cloud of smaller fragments, but usually a burst of gamma rays carrying away the energy, momentum, and other conserved quantities in a very orderly way. It is one of the cleanest transformations in all of physics, and also one of the easiest to misunderstand. The first misunderstanding comes from the everyday meaning of destruction. In ordinary life, when one thing destroys another, there is usually debris. A plate shatters into shards, a building comes down into dust and twisted steel, a tree burns into ash, smoke, and heat. The original object is gone, but its material has not vanished from the universe. It has simply changed form. In particle physics, annihilation is also a change of form, but the forms involved are stranger than common sense expects. The electron and the positron are not smashed into pieces the way two stones might be crushed together. They are converted into radiation through a process allowed by the laws of quantum field theory. Their mass, motion, and quantum numbers are redistributed into outgoing photons. Nothing has gone missing. What has changed is the way the energy is stored. This is an important point to hold on to because the word annihilation invites the wrong picture if left on its own. It suggests that the particles fall into a hole of nothingness. That is not what happens. Energy is conserved, momentum is conserved, electric charge is conserved, angular momentum is conserved. The event is not a cosmic tantrum. It is a transition from one allowed physical state to another. The electron and positron cease to exist as those particles, yes, but the universe does not tear up its accounting. The outgoing radiation carries the record of what occurred. To see why the electron and positron are such natural partners in this process, it helps to remember how closely matched they are, same mass, same spin. Opposite electric charge, opposite lepton number. They are in a deep sense mirror forms of the same underlying field structure. That is why their meeting is so special. They are not just two different particles bumping into one another by chance. They are particle and antiparticle, and the theory connects them very tightly. Their charges cancel. Their lepton numbers cancel. Under the right conditions, there is no obstacle to their energy being carried away by photons instead. Still, even here, physics is fussy about details. You cannot just say they meet and vanish and leave it at that, because the exact outcome depends on the circumstances. In the simplest idealized picture, an electron and positron annihilate to produce two gamma-ray photons. Why two? Because a single outgoing photon would generally fail to satisfy momentum conservation in the frame, where the pair started with no net motion. Two photons flying off in opposite directions can carry away the right amount of energy and balance the momentum cleanly. This is one of those moments where nature reveals itself to be much more disciplined than casual language makes it sound. Annihilation is not a matter of two particles disappearing and leaving a vague flash behind. It is a tightly constrained event with exact permitted outcomes. There are other possibilities too. Under some conditions, more than two photons can be produced, and the details depend on the quantum state of the system before annihilation. but the basic principle remains the same. The electron and positron do not dissolve into nothing. They transform into electromagnetic radiation in a way that preserves the rules of the theory down to the last measurable detail. The photons are not an afterthought. They are the lawful continuation of the process. If that makes annihilation sound less mysterious, good, but it should not make it sound ordinary. It is still one of the most striking things in physics because it challenges the old instinct that matter must be built from permanent little lumps. If you imagine the electron and positron as tiny solid beads, annihilation feels almost impossible. Where did the beads go? How can objects simply stop being objects? But in the field picture, the process is far easier to grasp. The electron and positron are excitations of a quantum field. The photons are excitations of another field. The interaction between fields allows one set of excitations to be converted into another. Once you see it that way, annihilation stops looking like a metaphysical scandal and starts looking like a very direct example of how the world is organized at small scales. There is another reason this process matters so much. It is not just some rare trick in a particle laboratory. The meeting of matter and antimatter is a general feature of the universe whenever particle-antiparticle pairs exist in the same region and have the chance to interact. In the early universe, this must have happened constantly. Electrons and positrons were being created from energetic radiation and annihilating back into photons in enormous numbers. The cosmos was not yet the comparatively calm place we now inhabit. It was hot, dense, and fast enough that the boundary between matter and radiation was much more fluid. In that setting, annihilation was not a special event. It was part of the ongoing traffic of reality. That historical fact gives the process a wider significance. It is not just about what happens when a positron meets an electron in a detector or in a medical scanner. It is about how the universe itself once behaved when conditions were extreme enough for matter and antimatter to trade places with radiation almost freely. If anything, our quiet modern world is the unusual case. The early universe was the more honest display of what the laws can do when enough energy is available. Closer to home, though, annihilation is something physicists can observe in detail. A positron produced in a radioactive decay or energetic interaction travels through matter, losing energy as it goes. Because it is positively charged, it is attracted to electrons and repelled by atomic nuclei. It does not usually wander for very long on human scales, though in microscopic terms its path can still be quite intricate. It slows down through repeated interactions, and eventually it encounters an electron in a state where annihilation becomes likely. When that happens, detectors can register the outgoing gamma rays. The event is not guessed at, it is measured. There is a very elegant intermediate stage that can occur before the final annihilation, and it deserves some attention because it reveals how subtle this whole business really is. Under the right conditions, an electron and positron can briefly form a bound state known as positronium. This is one of the more charming systems in particle physics, partly because it is so simple and partly because it is so short-lived. The electron and positron orbit their common centre of mass, rather than one heavy particle sitting still while the lighter one circles it. Since their masses are equal, the dance is more balanced than in an ordinary atom like hydrogen. Positronium behaves a bit like an atom, but only temporarily. It is not built to last. What makes positronium so interesting is that its lifetime and decay pattern depend on the spin arrangement of the electron and positron. If their spins line up one way, the state tends to decay into 2 photons. If they line up another way, it tends to decay into 3 photons. This is not a decorative complication. It is a reminder that quantum rules govern even the final moments of the pair with precision. The universe does not say merely that matter and antimatter cancel. It says they cancel in specific allowed ways depending on the exact quantum state. Even destruction, if we insist on calling it that, is subject to good manners. This is one of the reasons annihilation became such a fruitful subject for both theory and experiment. It is simple enough to be studied cleanly. but subtle enough to test deep features of quantum electrodynamics, the theory describing how charged particles and light interact. When physicists compare theoretical predictions for electron-positron processes with actual measurements, the agreement is often astonishing. The very fact that annihilation can be predicted so accurately is part of what makes modern physics so compelling. The process is dramatic, yes, but it's not chaotic. It fits inside a mathematical framework that works with extraordinary precision. At the same time, the word mystery still earns its place, though not because annihilation is lawless. It remains mysterious in a more philosophical sense because it forces us to confront what we really mean by a thing existing. In daily life, we think of objects as enduring carriers of identity. A chair remains a chair until it is broken. A coin remains a coin until it melts. But the electron and positron show us a different style of reality. Their existence is real, measurable, and fully physical, yet it is not permanent in the old material sense. They can be created from energy and later converted back into energy carried by radiation. Their identity is stable only within a web of allowed interactions. In other words, they are real, but not indestructible objects in the classical sense. That can feel slightly unsettling at first, because it undercuts the old fantasy that matter must rest on eternal little nuggets of stuff. The truth seems more dynamic. The world is built from fields, excitations, and transformations. Some patterns are stable for a long time, others are fleeting. The electron itself is stable in ordinary physics, but the positron in a matter-filled environment is not. It will almost always find an electron sooner or later, and when it does, the pair will cease to exist as particles and continue as photons. What persists most fundamentally is not the little objects themselves, but the conservation laws and the field structure that govern all these changes. There is a kind of emotional clarity in that if one is in the mood for it. Annihilation sounds absolute, but in fact it is one of the clearest examples that physics does not traffic in absolute endings. It traffics in transformation. The electron and positron are gone as electron and positron, but the event leaves behind radiation that can be detected, measured, and used. Hospitals rely on it in positron emission tomography, where the annihilation photons reveal information about processes inside the body. Astrophysicists look for annihilation signatures in space. Particle physicists build entire experiments around electron-positron interactions. The event is not a disappearance into silence. It is a conversion that leaves a very bright trace. Another common misunderstanding is to imagine antimatter as some kind of evil mirror of matter, inherently destructive, and somehow fundamentally opposed to existence itself. This is more science fiction than physics. Antimatter is not cursed matter. It is matter's partner under certain symmetry rules. A positron is not malicious. It is simply a positively charged antiparticle that, in a matter-dominated environment, does not have a stable long-term place because electrons are abundant. If our world had been built differently, with antimatter dominating and matter scarce, we would probably regard the positron as ordinary and the electron as the dangerous visitor. The drama is not built into morality. It is built into abundance and interaction. That point matters because it keeps the subject grounded. Matter and antimatter annihilate not because they hate one another, but because the laws of physics allow a lower particle count state with the same conserved quantities carried by radiation. The universe is not taking sides. It is simply following the rules available to the system. Once again, the field picture rescues us from misleading emotional language. The electron and positron do not cancel like opposing opinions in a committee meeting. They transform according to a permitted quantum interaction. One of the more interesting things about annihilation is how it reveals both symmetry and asymmetry at once. The symmetry lies in the exact matching between particle and antiparticle. Same mass, same spin, opposite charge. The asymmetry lies in what kind of world we live in. Since ordinary matter dominates our surroundings, positrons are temporary arrivals while electrons are everywhere. That means annihilation feels like the fate of the positron much more than the fate of the electron. even though the process consumes both. The difference is not in the law, but in the environment. This is a recurring lesson in physics. What feels normal to us often reflects cosmic history rather than deep necessity. There is also something mathematically satisfying about how neatly annihilation closes the loop with pair production. Earlier we considered how high-energy light can create an electron and a positron. Annihilation is the reverse channel. The pair returns to light. That reversibility is not just aesthetically pleasing, it is part of the logic of quantum field theory. Fields interact, excitations can be traded, matter and radiation are connected by lawful processes that work in both directions when conditions allow. The positron is a kind of ambassador of that deeper truth. Its life story often begins in energetic creation and ends in energetic reconversion. If one lingers on that too long, it becomes hard not to admire how direct the lesson is. Matter is not a dead inventory of stuff sitting around forever. It is an active participant in a network of transformations. The positron, perhaps more clearly than many particles, shows this because its existence in ordinary matter is almost always temporary. It appears, travels, slows, encounters an electron and annihilates. The whole sequence reads like a compact demonstration of modern physics. First fields produce the pair, then charge guides the motion. Then quantum interaction closes the process in a burst of photons. None of this removes the emotional charge of the word annihilation entirely, and perhaps it should not. Part of the power of science comes from keeping a little of the shock while deepening the understanding. Yes, the electron and positron vanish as particles. Yes, their mutual existence can end in a very literal sense. But what replaces them is not emptiness. It is radiation, measurable and precise, carrying forward everything the laws require. The event is dramatic without being mystical, final without being absolute, destructive without being lawless. And yet, even after we understand the process, another question starts to tug at the edge of the story. Why was physics ready for such a thing at all? Why were scientists prepared to accept that a particle could have an exact opposite, and that the pair could be created and annihilated in such a mathematically clean way? That readiness did not come from common sense. It came from theory, and especially from one extraordinary equation that did not merely describe the electron more accurately, but opened the door to antimatter itself. To understand why annihilation is not just a curiosity, but part of a deeper order, we have to go back to the moment when the mathematics first hinted that nature might contain a mirror electron waiting to be found. To understand why physicists were eventually willing to accept the positron as something real, and not just a mathematical nuisance, we have to return to a moment when theory was under pressure. By the late 1920s, the old picture of the electron was no longer enough. Quantum mechanics had been developing rapidly and with impressive success. It could explain atomic structure, energy levels, and a number of effects that classical physics had simply failed to handle. At the same time, Einstein's special relativity had already shown that space and time had to be treated together, and that high-speed motion did not obey the comfortable rules of older mechanics. Both theories were powerful. Both were right within their domains. But the electron lived in both worlds. It was a quantum object, and it could move fast enough that relativity mattered. So the question became unavoidable. Could one write down a theory of the electron that took both quantum mechanics and relativity seriously from the start? This was not a decorative problem, and it was not the kind of difficulty one could smooth over with clever wording. If physics wanted a truly modern description of matter, it needed an equation that would treat the electron properly in a relativistic quantum framework. The challenge was that earlier attempts ran into trouble. Some produced results that didn't match observation well enough. Some seemed to mishandle key properties of the electron. Some missed an important feature altogether, namely spin, which by then had emerged as one of the fundamental characteristics of the electron. Spin is not quite like a little ball literally rotating in space, though the name invites that picture. It is an intrinsic quantum property, and it mattered deeply in the behaviour of electrons. So a successful theory had to do several things at once. It had to be quantum. It had to be relativistic. It had to account naturally for spin. And it had to make physical sense. Paul Dirac approached the problem with the kind of severity that often produces beautiful physics. He did not want a patched-up compromise. He wanted a deeper equation, something structurally right, something that would not merely imitate the facts, but explain why the electron had the properties it did. That ambition is worth dwelling on because it captures a certain style of theoretical physics at its best. The goal is not just to fit data like a tailor fixing a coat after it keeps tearing at the elbow. The goal is to find the form the laws themselves seem to prefer. When Dirac succeeded, the result was extraordinary. His new equation described the electron in a way that incorporated relativity and quantum theory together. It also accounted for the electron's spin in a natural manner, rather than adding it by hand afterward. That alone would have been a major achievement. But the equation had a further surprise waiting inside it, and this is where the dream of antimatter begins. The equation did not just allow the expected electron states, it also contained solutions corresponding to negative energy. That was not a minor inconvenience. It looked like a serious conceptual problem. If electrons could occupy arbitrarily low negative energy states, then matter as we know it would be unstable. An ordinary electron ought to tumble downward endlessly, shedding energy forever. The world would be an absolute catastrophe of runaway collapse, and since our world was clearly not behaving like that, something had to give. Either the equation was wrong, or the interpretation of the equation was incomplete. This is one of those moments where scientific imagination has to decide whether to retreat or advance. A less daring mind might have tried to ignore the unwanted solutions, treat them as mathematical rubbish, or tinker with the framework until the discomfort went away. Dirac did something harder. He took the equation seriously enough to assume that the odd feature might be telling him something true about the world, rather than something false about the mathematics. That is a dangerous move in science if done carelessly, but when it is done by someone with strong judgment, it can change history. Dirac's first interpretation was strange, though perhaps no stranger than the problem itself. He proposed that all the negative energy states were already filled in a kind of invisible background sea. Because of the exclusion principle, ordinary electrons could not simply fall into those occupied states. That saves stability. But it introduced a new possibility. If one of those states were vacant, the absence would behave like a positively charged particle. In modern terms, this was a stepping stone toward the idea of the positron, though Dirac himself did not immediately leap to the fully correct interpretation as quickly as textbooks now make it seem. At first, he wondered whether this positively charged counterpart might be the proton. After all, the proton was already known, and it carried positive charge. But that identification soon ran into trouble. The proton is far heavier than the electron. Dirac's framework pointed toward a particle with the same mass as the electron, not a much heavier one. In other words, the mathematics was not hinting vaguely at positivity in general. It was demanding a specific mirror of the electron itself, same mass, opposite charge, same kind of relativistic quantum existence. That was the astonishing step. It is difficult now, after generations of exposure to particle physics, to recover the full oddness of that moment. The idea that every particle might have an antiparticle partner sounds almost routine in modern science. It appears in school books and documentaries. It turns up in films, usually with more explosions than necessary. But at the time, this was a bold and unsettling thought. Nature had already surprised physicists many times in the early 20th century, but this was a very particular sort of surprise. The theory was not merely permitting a strange new particle, it was demanding one in order to remain internally coherent. That is one reason the positron matters so much historically. It was not discovered first and then explained later as a lucky accident of experiment. In an important sense, it was dreamed by theory before it was photographed in the laboratory. That gives the whole episode a rare and satisfying structure. Mathematics, when handled with unusual physical insight, reached beyond the already observed world and found room for something new. Then, experiment came along and confirmed that the room was occupied. The word dream in this context should not be taken to mean fantasy. Dirac was not daydreaming in the ordinary sense. He was following the logic of an equation so carefully that it began to reveal a reality broader than familiar matter. But dream still feels like the right word in another sense, because the idea of antimatter did have a quality of imaginative expansion about it. It suggested that the world might be built with a deeper symmetry than anyone had fully grasped. Matter did not stand alone. It came with reflections. The known particles might not be the whole cast. There could be opposites, partners, mirror forms built into the architecture of the laws themselves. This is one of the reasons the Dirac equation occupies such an honoured place in physics. It was not just technically successful, it was fertile. It opened conceptual space. It suggested that a correct equation can do more than organise known facts. It can reveal hidden possibilities that the universe has been keeping in reserve. That is one of the most thrilling things theoretical physics can do when it's working properly. It can show that the logic of the world outruns the current inventory of observation. There was another important feature of the equation that deepened its influence. It did not merely predict a new particle. It also made the connection between symmetry and particle identity feel more profound. The positron was not just another positively charged object in nature. The proton already had that role in one sense. The positron was the electron's antiparticle. That was a much stronger relationship. It told physicists that particle properties were not just a jumble of labels. They could be organised through transformations, oppositions, and deep structural relationships within the theory. This mattered enormously for the development of quantum field theory. Once physicists began to understand particles as excitations of underlying fields, the appearance of antiparticles ceased to seem like a bizarre side effect and became part of the basic language. In that newer picture, the electron and positron are tied to the same underlying field. The positive and negative energy puzzle that had seemed so awkward in the older interpretive scheme found a more natural home. The positron was no longer a hole in an invisible sea in the literal sense Dirac first imagined. It became the positive energy antiparticle state, associated with the relativistic quantum field of the electron. That later reinterpretation is important because it shows how physics often advances. A brilliant idea may arrive in a form that is not quite the final one. Dirac's sea picture helped him and others think through the problem, but the modern understanding moved beyond it. This is not an embarrassment to the theory. It is how deep scientific progress usually works. The first conceptual scaffolding is sometimes removed once the structure stands more securely on its own. What remains is the achievement itself. Dirac found the framework that forced physicists to take the positron seriously. There is also something quietly remarkable about how elegant the equation turned out to be compared with the scale of its consequences. It did not announce antimatter with trumpets, it simply refused to avoid it. The mathematics had a kind of discipline that made the result feel inevitable once seen clearly. That sense of inevitability is often a mark of powerful theory. What looked outrageous at first begins to feel unavoidable afterward. By the time the positron was experimentally confirmed, Dirac's strange prediction was no longer just a speculative leap. It had become a coherent piece of a broader picture, and then the experimental confirmation arrived, which changed the mood completely. Carl Anderson's cloud chamber images showed a positively charged particle with the same mass as the electron. The mirror had been found. Theory and experiment locked together. The abstract possibility became physical fact. At that point, antimatter stopped being a dream in the sense of being merely imagined. It became part of the actual world. Still, the dream did not end there. In a way, it expanded. Once the positron was real, physicists naturally began to wonder whether other particles also had antiparticles. That suspicion proved correct. Antimatter was not a one-off miracle attached only to the electron. It appeared to be a general feature of the framework. Particle physics became richer, more symmetric, and more conceptually daring as a result. One could now speak not just of a single antiparticle, but of whole families of particle-antiparticle relationships. The universe seemed to be written in a more balanced grammar than before. At the same time, this raised a new puzzle, one that still lingers over cosmology. If matter and antimatter are so naturally paired in the laws, why does the visible universe appear to contain far more matter than antimatter? Why are we not living in a cosmos where matter and antimatter exist in equal large-scale amounts, constantly meeting at the boundaries and annihilating in magnificent bursts of radiation? Somewhere between the deep symmetry of the equations and the actual history of the cosmos, an asymmetry emerged. The Dirac equation opened the door to antimatter, but it also sharpened the mystery of why our world seems so one-sided. That is one of the reasons the positron remains such a powerful teaching particle. It is small, specific, and very concrete, but it points outward toward enormous questions. It tells us that theory can predict new reality. It tells us that particle identity has a mirror structure. It tells us that matter is not the only way the basic fields can express themselves, and it hints that the early universe must have been a place where these possibilities were alive in abundance. There is a broader lesson here about what equations are in physics. Outside science, an equation often looks like a compressed piece of technical shorthand, useful perhaps, but emotionally empty. Inside physics, the right equation can be something more like a map with regions not yet explored. It can reveal hidden terrain. Dirac's equation did not just summarize known behavior. It contained a promise, or perhaps a warning, that the known world was not complete. The electron had an opposite weighting in the logic. Physics did not invent the positron by whim. It uncovered it by listening carefully to what the theory insisted upon. That is why this story has remained so attractive to physicists. It is one of the cleanest examples of successful theoretical courage. Dirac trusted the mathematics enough to follow it somewhere unfamiliar. Experiment then caught up and confirmed that unfamiliar place was real. The sequence flatters neither theory nor experiment alone. It flatters the partnership between them. The dream of antimatter was not a triumph of imagination against evidence, nor of measurement without thought. It was a triumph of their cooperation. There is also a more philosophical comfort in it, though perhaps comfort is not quite the right word. The story suggests that the universe is not random in its strangeness. It is strange with structure. The positron is not a theatrical gimmick added for surprise. It grows out of a coherent framework. Antimatter is weird, yes, but it is weird in a lawful way. That distinction matters. Science does not simply collect marvels, it tries to show that the marvels belong together. Even now, long after the first discovery, the Dirac equation still stands as a reminder that the line between mathematics and physical reality can sometimes be thinner than expected. This does not mean every elegant formula reveals a hidden particle. Physics is not a wishing well for beautiful ideas. But when a theory is grounded, constrained, and experimentally accountable, its mathematics can reach farther than intuition. Dirac's achievement is one of the strongest historical examples of that reach, and from the point of view of the positron itself, the whole story gives it a special status. The positron was the first antiparticle to be discovered, the first clear sign that nature's inventory includes these mirrored partners. It was the doorway through which antimatter entered the real world of experiments, detectors, and practical applications. The dream became a trace in a cloud chamber, and then a standard part of the universe as described by physics. Once that happened, the positron stopped being merely the answer to a theoretical puzzle. It became a tool, a signal, a messenger. Physicists began to find it in cosmic rays, in radioactive decays, in high-energy collisions. It appeared not only in equations and laboratories, but in space itself. The mirror electron was not confined to abstract theory or specialized machines. It was out there in the cosmos, produced in violent astrophysical environments and travelling across regions far larger than any human scale. And that naturally leads the story onward, because once antimatter had been accepted as part of the fabric of physics, the next question was no longer whether the positron existed, but where the universe was making them, how often, and what their presence could tell us about stars, explosions, and the energetic history of space. And that is where the story widens quite naturally, because once the positron was accepted as a real particle, and not just a mathematical curiosity, physicists had a new question on their hands. If nature allows positrons to exist, where exactly is it making them? The laboratory could produce them, radioactive nuclei could emit them, high-energy photons could generate them in pair production. But the universe is much larger and far less tidy than any laboratory, and it does not wait for us to switch on the equipment before carrying out its own experiments. Long before cloud chambers and particle detectors, space was already producing positrons in violent, energetic environments and sending them across enormous distances. In that sense, the positron is not just a lesson in theory, it is also a traveller, a byproduct of stars, explosions, and cosmic radiation moving through the galaxy. The first place to look is where nature has plenty of energy to spare, because positrons do not tend to appear in calm and ordinary settings. They are not the sort of particle that drifts lazily out of a cool rock or a quiet cloud of gas without some specific process driving their creation. Space, however, contains many such processes. Stars fuse nuclei in their cores. Supernovae blast matter outward at astonishing speeds. Pulsars spin and generate fierce electromagnetic fields. Black holes and neutron stars create extreme conditions in their surroundings. High-energy cosmic rays strike atoms and trigger showers of secondary particles. In all of these places, energy is being moved around on scales that make particle creation possible, and positrons can emerge as part of the resulting chain of events. One of the cleaner routes by which stars can produce positrons involves radioactive nuclei. In certain nuclear reactions, unstable isotopes are formed, and some of those isotopes can undergo beta plus decay. In that process, a proton inside the nucleus changes into a neutron and emits a positron along with a neutrino. This is not the most familiar aspect of stellar life for people outside astrophysics, because when we think of stars, we tend to imagine steady shining, rather than a complicated inventory of short-lived nuclei. But stars are not just glowing balls of simple gas. Their interiors and explosive deaths involve nuclear reactions that produce a whole zoo of isotopes, some of them unstable and eager to decay. When those decays happen, positrons can be among the products. This becomes especially important in explosive stellar events such as supernovae. A supernova is not merely a star getting a bit brighter and then calming down again. It is a violent transformation of stellar structure, releasing immense amounts of energy and forging many new nuclei in the process. Among the debris of such explosions are radioactive isotopes that can decay by emitting positrons. Those positrons then move through the expanding material, lose energy, and eventually annihilate with electrons producing gamma rays. In this way, the positron becomes part of the observable aftermath of stellar destruction. The star dies, new elements are scattered into space, unstable nuclei decay, positrons appear, and their annihilation leaves a signal that astronomers can search for. That chain matters because it gives astrophysicists a way to study processes they cannot touch directly. No one is going to lean casually over a supernova remnant with a notebook and a thermometer. The information has to come to us in the form of light and radiation. Positrons and their annihilation signatures are part of that information. When astronomers detect gamma rays at energies associated with electron-positron annihilation, they are not just seeing an isolated particle event. They are seeing evidence of the kinds of processes that have been taking place in remote and energetic parts of the galaxy. There is a particularly famous line of evidence tied to this. When an electron and positron annihilate under common astrophysical conditions, the resulting gamma rays can carry a very specific energy signature. observations of the galaxy have revealed such annihilation radiation, especially coming from the central regions. This has been a major clue and also a long-running puzzle, because it tells us that large numbers of positrons are being produced somewhere in or around the galactic environment. The challenge is to work out exactly which sources are responsible and in what proportions. Supernovae are certainly candidates. Radioactive decay in stellar remnants is a candidate. Compact objects such as pulsars are candidates. Interactions of cosmic rays with interstellar matter can also play a role. The galaxy appears to be producing positrons in several ways, and sorting out the details has kept astrophysicists usefully busy for quite some time. Pulsars are especially interesting in this story because they are among the most extreme regular objects in the universe. A pulsar is a rapidly spinning neutron star, the collapsed core left behind after a massive star ends its life in a supernova. Neutron stars pack more mass than the Sun into a region only a few tens of kilometers across. Their magnetic fields can be immense, and their rotation can be astonishingly fast. Under those conditions, the electromagnetic environment around the pulsar can become so intense that particle acceleration and pair production occur readily. Electrons and positrons can be created in large numbers in the magnetosphere, the region dominated by the star's magnetic field. These particles may then be flung outward at high energies, contributing to the surrounding nebula and perhaps to the population of cosmic positrons detected farther away. This is one of the reasons pulsars have become important in discussions of high-energy cosmic radiation. They are natural particle accelerators, and unlike human-built accelerators, they do not need funding committees, maintenance crews, or coffee breaks. Their magnetic and electric fields can accelerate charged particles to tremendous energies, and in the process they can generate cascades in which photons create electron-positron pairs, and those particles in turn emit more radiation. The result is a busy environment rich in high-energy electrons and positrons. From our point of view on Earth, this means that at least some of the positrons measured in cosmic radiation may have begun their lives near these compact stellar remnants. Cosmic rays themselves add another path to the story. Cosmic rays are energetic particles, mostly protons and atomic nuclei, moving through space at very high speeds. When they collide with atoms in the interstellar medium or with the atmosphere of a planet, they can produce showers of secondary particles. Among those secondaries can be positrons. This means that the universe does not need to manufacture every positron directly in a star or compact object. Some are produced later as energetic cosmic rays strike matter and trigger chains of interactions. The same basic physics seen in laboratory particle collisions is at work on a larger stage. High-energy particles hit targets. New particles appear. Positrons join the mix. This becomes particularly relevant when instruments above the atmosphere or in space detect unexpected amounts of high-energy positrons. Over the years, measurements of cosmic radiation have shown that the positron content at certain energies is not quite as simple as one might expect from the most basic models of secondary production alone. That has led scientists to consider additional sources, including nearby pulsars and other energetic astrophysical environments. In more speculative discussions, some have even wondered whether unusual sources such as dark matter interactions could contribute. Whether or not those more exotic ideas survive, the essential point remains solid. Space is not empty and quiet in the particle sense. It is full of energetic processes that can produce positrons and send them across the galaxy. It is worth appreciating just how strange that is from the perspective of ordinary life. We tend to think of space as a large emptiness with a few stars placed here and there like lights on a dark ceiling. In reality, it is an active medium filled with radiation, magnetic fields, plasma, shock waves, and fast-moving particles. It is less like a silent vacuum and more like a very thin but very energetic weather system, operating over enormous distances. In that environment, positrons are not absurd intruders. They are natural products of the conditions. Black holes and the regions around them also deserve mention, though with some care. A black hole itself is not a factor in the simple sense, since what matters most for observable processes is usually the environment around it. Matter falling toward a black hole can become extremely hot and energetic before crossing the event horizon, especially in the presence of accretion disks and strong magnetic fields. In such surroundings, high-energy photons and accelerated particles can create electron-positron pairs. Similar things can happen in the jets launched from the vicinity of black holes in some systems. These jets can travel enormous distances and contain highly energetic particles. Whether positrons make up a significant fraction of the particles in a given jet is a subject that depends on the detailed astrophysics, but the broader principle is clear enough. Regions around compact objects can be energetic enough for pair creation to occur and for positrons to be produced in abundance. There is also the Sun, which on one hand is much calmer than a pulsar or supernova, and on the other hand is still a star with plenty of energetic tricks available under the right conditions. In its core, the nuclear reactions that power the Sun include steps in which positrons appear. One of the key fusion pathways that converts hydrogen into helium involves the creation of positrons. These positrons do not travel out into space from the core in any direct simple way, because the solar interior is dense and the particles interact quickly. They annihilate locally. But their existence in the fusion chain is important, because it reminds us that positrons are not limited to the most exotic corners of the cosmos. Even the ordinary star that warms your face on a clear day relies in part on processes that involve positrons deep in its interior. That is a useful correction to intuition. Positrons feel exotic to us because they do not survive for long in the matter-filled world around us. But from the standpoint of nuclear and high-energy astrophysics, they are simply one of the allowed outcomes nature uses when conditions call for it. They are part of the standard machinery, not a special effect added for dramatic flair. Still, what happens after they are produced is often just as important as how they are born. A positron moving through space does not always travel in a straight line like a neat little courier on a simple route. Interstellar space contains magnetic fields, diffuse gas, dust and radiation. Charged particles spiral around magnetic field lines, scatter, lose energy, and wander through complicated paths. A positron born in one location may annihilate somewhere else entirely after slowing down over time. That complicates the astrophysical detective work. When we observe annihilation radiation from a region, it does not always point neatly back to the exact source that created the positrons. The particles may have travelled, scattered, and mixed with the surrounding environment before meeting electrons and vanishing. This is part of why the galactic positron problem has been so interesting. Observers can detect the signature of positron annihilation, but explaining the distribution of that signal requires not only identifying likely sources, but also understanding how positrons propagate through interstellar space. Do they travel far before slowing down? Are they mostly confined near their birthplaces? Do magnetic fields channel them into certain regions? How much do supernova products contribute compared with pulsars or other compact sources? These are not trivial questions, and the answers depend on a mix of nuclear physics, plasma physics, astrophysics, and careful observation. There is a modest comedy in the fact that a particle so tiny can become such a large-scale problem. One might expect galactic astronomy to concern itself mainly with stars, nebulae, and black holes, not with the fate of a particle whose lifetime in ordinary matter may be very short. And yet the positron manages to matter on both scales at once. It is born in nuclear and particle processes, but its collective presence leaves signatures across the structure of the galaxy. It is one of those cases where the very small and the very large are tied together more tightly than common sense expects. Cosmic radiation measured near Earth gives another window into this. Detectors carried on balloons, satellites, or space stations can count and classify high-energy particles arriving from space. Among them are positrons. Not many compared with the total flood of cosmic particles, but enough to study. By examining how the positron fraction changes with energy, scientists can learn about the astrophysical sources contributing to the cosmic ray population. If all positrons came only from secondary collisions of cosmic rays with interstellar matter, one pattern would be expected. If nearby pulsars or other primary sources contribute, the pattern can change. So the positron becomes part of a forensic investigation into what is happening in the local galactic neighbourhood. There is also a deeper cosmological shadow hanging over all this. In the early universe, positrons were not rare at all. When temperatures were high enough, electrons and positrons would have been in near constant creation and annihilation with radiation. As the universe expanded and cooled, most of those pairs annihilated away, leaving behind the small excess of ordinary matter that would eventually form stars, planets, and us. That means every positron observed today is in some sense a local reappearance of a particle that was once part of the early thermal life of the cosmos. The universe started in a state where matter and antimatter were far more evenly present. The fact that we now detect positrons mainly in specific energetic environments tells us how much conditions have changed, and that gives the positron a curious role in astronomy. It is both ordinary and unusual. Ordinary because the laws of nature produce it whenever the conditions are right. Unusual because our present universe is matter-dominated enough that positrons usually appear only in energetic niches, rather than as permanent residents of bulk matter. In stars, explosive remnants, pulsar magnetospheres, cosmic ray interactions, and perhaps around compact objects, those niches are available. The result is a scattered but persistent population of positrons moving through space, annihilating in some regions, escaping in others, and leaving detectable clues behind. From a storytelling point of view, the positron is almost too useful. It begins in fundamental theory. It appears in the laboratory. It teaches the field picture. It demonstrates pair creation and annihilation. Then it turns up in stars, supernova, pulsars, and cosmic rays, as if determined to make itself relevant at every scale. There are particles in physics that feel specialized, living mostly in equations or highly controlled experiments. The positron is not one of them. It belongs to the deep theory and the real sky at the same time. That combination is part of what makes it so satisfying to follow. When an astronomer studies annihilation radiation from the galaxy, they are not doing something entirely separate from particle physics. They are reading the consequences of the same positron that first emerged from the logic of the Dirac equation and the tracks of a cloud chamber. The difference is only one of setting. In one case, the stage is a detector in a laboratory. In the other, it is the galaxy itself. And once we notice that, another shift in the story begins to suggest itself. The positron is not only a clue about stars and cosmic radiation. It is also useful much closer to home in a very different context, because the same annihilation process that helps astronomers study the galaxy can also help doctors study the human body. That may sound like a sharp change of scene from pulsars and supernova remnants to hospitals and scanners, but the physics is continuous. The positron does not care whether it is born in a stellar explosion or in a carefully prepared medical tracer. It follows the same rules either way, and those rules can be turned into a way of seeing what would otherwise remain hidden inside living tissue. Once the positron leaves the grand settings of stars and cosmic radiation and enters the world of medicine, something very satisfying happens. A particle that helped reshape fundamental physics becomes useful in an intensely practical way. It stops being only a clue about the structure of reality and starts helping doctors answer a direct question. What is happening inside the body right now? Not in the rough sense of a guess, not by inference alone, but by tracing real biological activity in living tissue. That is one of the quiet strengths of modern science. The same rules that describe annihilation in deep space can also help reveal whether a region of the brain is active, whether heart tissue is still receiving blood, or whether a tumour is consuming energy in a suspicious way. The key technology here is positron emission tomography, usually shortened to PET. The name sounds technical. and it is, but the basic idea is surprisingly clear once you unpack it slowly. A tiny amount of a radioactive substance is introduced into the body. That substance is chosen so that as it decays, it emits positrons. Those positrons do not travel very far before meeting electrons in nearby tissue. When that happens, positron and electron annihilate, and the annihilation produces gamma rays that fly off in opposite directions. A PET scanner detects those gamma rays and uses them to reconstruct where inside the body the positron emission took place. In other words, the machine does not see the positron directly in the way one might watch a bird cross the sky. It sees the aftermath of the positron's short life, and uses that information to build an image. That already tells you something important about the whole method. PET is not mainly about showing anatomy in the old simple way, like drawing the outline of bones or organs. It is more about showing activity. It tracks where a specially chosen substance goes and where it is being used. That means PET can tell you something about metabolism, blood flow, receptor binding, and other living processes. It does not simply tell you what is there, it tells you what is happening. That distinction is one of the reasons it became so valuable in medicine. To understand why the positron is so useful in this setting, it helps to think about the problem doctors face. The body is full of organs and tissues that can look similar in shape while behaving very differently. A tumour, for example, may not always stand out clearly just because of its shape, especially in its early stages. But many tumours consume glucose at unusually high rates because their cells are dividing rapidly and demanding energy. A PET scan can exploit that fact by using a tracer related to glucose. The tracer is taken up by active tissues, and because it contains a radioactive atom that emits positrons, the scanner can map where it accumulates. Areas of unusually high uptake may then suggest abnormal biological activity. This is where the story becomes especially pleasing from a physics point of view. The positron is useful not because it survives for a long time, but because it does not. Its short journey through tissue and its predictable annihilation are exactly what make it informative. Once emitted, the positron travels a short distance, losing energy as it passes through nearby matter. Because tissue is full of electrons, the positron quickly finds a partner and annihilates. That annihilation produces two gamma-ray photons moving in nearly opposite directions. If a ring of detectors around the patient picks up those two photons at almost the same time, the scanner knows that the annihilation happened somewhere along the line connecting the detectors. By collecting vast numbers of such events and using reconstruction algorithms, the system can estimate where the radioactive tracer is concentrated inside the body. There is something almost elegant about how little the scanner needs to know directly. It does not follow the positron inch by inch. It does not watch the tracer atom itself with a little magnifying glass. It waits for the annihilation photons, then uses timing and geometry to work backward. That is a very modern scientific style. You detect the consequences of a process and reconstruct the hidden event from the evidence. In that sense, PET belongs to the same family of thinking as particle physics and astronomy. You cannot reach in and point at the exact event as it happens, but you can detect the signals it leaves and infer the underlying process with remarkable accuracy. The radioactive substances used in PET are called radio tracers. The word tracer is important because the amount used is typically very small. The purpose is not to flood the body with some active drug effect, but to tag a biological pathway so its distribution can be followed. The radioactive part of the tracer comes from an isotope that decays by emitting a positron. One of the most common examples uses a form of fluorine attached to a glucose-like molecule. Cells take up the molecule in a way similar to glucose, but once inside it becomes trapped in a form that allows its accumulation to reflect metabolic activity. Since many cancers consume glucose rapidly, this tracer can highlight tumours or metastases that might otherwise be difficult to detect. That does not mean PET is only for cancer. It is widely used there, but its usefulness extends much further. In neurology, PET can help reveal patterns of brain metabolism and blood flow. Different regions of the brain have different activity levels depending on what they are doing and whether disease is affecting them. In disorders such as Alzheimer's disease, certain patterns of reduced metabolism can appear. In epilepsy, PET can help identify areas of abnormal brain activity that may relate to seizure origin. In research settings, PET can also be used with tracers designed to bind to specific receptors or proteins, allowing scientists and clinicians to study the living chemistry of the brain in ways that ordinary structural imaging cannot provide. In cardiology, PET can show whether regions of heart muscle are still viable. That's an important question when parts of the heart have been damaged by reduced blood supply. A region of tissue may be weak but not dead. If it is still metabolically active, treatment to restore blood flow may help it recover. PET can help distinguish tissue that is merely struggling from tissue that is permanently lost. That difference can guide major decisions about therapy. All of this depends on the special way positrons behave in matter. The positron's short path length is both a strength and a limitation. It is a strength because the annihilation happens close enough to the emission site that the resulting image can still reflect where the tracer was located. It is a limitation because the positron does travel some distance before annihilating, and that blur places a natural bound on spatial resolution. The image is not infinitely sharp. There is always some uncertainty introduced by the distance between the point of emission and the point of annihilation. Different radioactive isotopes produce positrons with different energies, and that affects how far they tend to travel before annihilating. Higher energy positrons usually travel farther, which can slightly reduce image precision. This is a good example of how medical imaging is never just about one clever idea. It is always a balance of physics, biology, engineering, and mathematics. The isotope must have a suitable half-life. The tracer must participate in the biological process of interest. The emitted positron energy must be manageable. The annihilation photons must be detectable. The detector system must have good timing and energy resolution. The reconstruction algorithms must be sophisticated enough to extract a meaningful image from noisy data. And the clinical interpretation must be careful, because high tracer uptake is not automatically a diagnosis. Inflammation, normal tissue activity, and other processes can also change tracer distribution. PET is powerful, but it is not magical. It works because many pieces cooperate. The detector ring in a PET scanner is designed to capture the annihilation photons as efficiently as possible. When the electron and positron annihilate, the resulting gamma rays move in nearly opposite directions. If two detectors on opposite sides of the scanner register a photon pair within a very short timing window, the system treats that as a coincidence event. That word coincidence sounds casual, but in imaging it has a very precise meaning. The machine is looking for two detections that are likely to have come from the same annihilation. Once enough of these events are collected, the scanner uses them to reconstruct a three-dimensional map of tracer distribution. One of the clever developments in modern PET is time-of-flight information. The idea is that if the scanner can measure the arrival times of the two photons with sufficient precision, it can estimate not only the line along which the annihilation occurred, but also something about where along that line it happened. The difference in arrival times is tiny, of course, because gamma rays move at the speed of light. But detector technology has improved enough that even very small timing differences can help. This improves image quality and reduces uncertainty. It is another reminder that the medical usefulness of positrons depends not only on nuclear physics, but also on painstaking advances in instrumentation. PET is often combined with other imaging methods, especially computed tomography or magnetic resonance imaging. This combined approach makes a great deal of sense. PET is excellent for showing function and metabolic activity, but its anatomical detail is limited compared with structural scans. A CT scan, for example, provides detailed information about physical structures, while PET shows where the tracer is active. Put them together and you get a more complete picture. A bright spot in PET becomes much more informative when it can be placed precisely within the anatomy shown by CT or MRI. This is why PET-CT scanners became so important clinically. They unite functional information with structural location. There is a nice conceptual symmetry in that too. The positron itself is a tiny messenger of function. It tells you not just that a tissue exists, but that it is taking up a tracer and doing something with it. The structural scan tells you where the tissue sits in the body. Together, they answer both questions at once. What is there, and what is it doing? The tracers used in PET can be tailored to different biological targets. A glucose analog is the most famous, but it is far from the only option. Some tracers are designed to follow blood flow, some bind to bone activity. Some target neurotransmitter systems in the brain. Some are used to study specific tumour features or to monitor the effects of treatment. This flexibility is one of the reasons PET has remained such a valuable tool in both medicine and research. The positron is always the physical messenger, but the biological question can change depending on the tracer chosen. That adaptability is also a reminder that the usefulness of PET is not just about the scanner. The chemistry matters enormously. A radio tracer must be produced, handled, and delivered before too much of it decays away. Many positron-emitting isotopes have quite short half-lives, which is both helpful and inconvenient. It is helpful because the radioactive exposure does not persist for long. It is inconvenient because the tracer must often be produced relatively close to where it will be used. Some medical centres have cyclotrons or access to regional facilities that can produce the isotopes. Here the story briefly circles back toward high-energy physics again. Machines built to accelerate particles can end up serving hospitals by creating the isotopes needed for PET imaging. The route from particle theory to clinical medicine is sometimes more direct than it first appears. Safety is naturally part of the story. Since PET involves radioactive materials, the amount used and the procedures surrounding it are carefully controlled. The doses are chosen to provide useful diagnostic information, while keeping exposure within medically acceptable limits. The fact that the tracers often decay fairly quickly is an advantage. The positron appears, annihilates, and the emitted photons are detected. The body then clears the tracer over time. This does not make the technique trivial, of course, but it does mean PET can be used routinely in many clinical settings when the information it provides is worth the exposure involved. There is another subtle point worth noticing. PET images are not direct photographs in the everyday sense. No tiny camera is looking at the tumour or the brain region the way one might look through a window. The images are reconstructions built from detected events. That means interpretation always involves statistics, modelling, and correction for various effects. Photons can scatter. Some events are missed. Some detected pairs are not true coincidences, but accidental ones. The body attenuates radiation differently in different regions. Modern PET systems correct for these factors with impressive sophistication, but the underlying truth remains. The image is an inference from many measured annihilation events. It is a highly reliable inference when done properly, but still an inference. That is not a weakness. It is simply the modern style of seeing. Much of science works this way. We rarely look at reality in a simple, unmediated fashion, especially when dealing with processes inside living tissue or at subatomic scales. We detect signals, model processes, and reconstruct hidden structures. PET is one of the clearest examples because the chain from invisible event to useful image is so well defined. A tracer enters the body. The isotope decays. A positron is emitted. It slows in tissue. It annihilates with an electron. 2 gamma rays fly outward. Detectors register them. Software reconstructs their origin. The clinician interprets the resulting map. At every step, the physics is specific. From the patient's point of view, all of this hidden complexity may feel surprisingly calm. They receive the tracer, wait while it distributes, lie still in the scanner, and later receive a report. The drama is all inside the mathematics and the biology. Tiny particles are being emitted and annihilated. Photons are crossing the body and striking detectors. Vast amounts of data are being processed into an image that may alter treatment plans or clarify diagnosis. Yet the human experience of the scan itself can be quiet and uneventful. That contrast feels very characteristic of science in its mature forms. The more extraordinary the unseen process, the more ordinary the outward procedure can become. One of the most powerful uses of PET in oncology is treatment monitoring. A tumour may change its metabolic activity before it changes much in size. That means PET can sometimes show whether a treatment is working sooner than methods that rely mainly on structural shrinkage. If tracer uptake falls, it may indicate that the tumour is becoming less active even before the anatomy changes dramatically. This can help clinicians decide whether to continue a therapy, adjust it, or consider alternatives. In that way, the positron contributes not only to diagnosis but to the timing and strategy of care. In neurology and psychiatry, PET has also served as a research window into the living brain. Different tracers can be used to study metabolism, blood flow, or receptor systems. That allows researchers to investigate how diseases affect brain chemistry and function in ways that are difficult to access otherwise. The brain is especially challenging because structure alone often does not tell the whole story. Two brains may look similar on a purely anatomical scan while behaving quite differently. PET adds another layer, letting scientists ask where energy is being used, which systems are active, and how those patterns change with illness or treatment. There is something profoundly satisfying about the fact that positron annihilation, which first sounds like a destructive event, becomes the very thing that makes the imaging possible. Without the annihilation photons, the scanner would have far less to work with. The positron's short life is what creates the detectable signal. In a sense, the particle helps us by ending in exactly the right way. It is a messenger whose disappearance delivers the message. That also makes PET a beautiful example of how fundamental physics can become practical without losing its conceptual depth. The scan works because the positron is the electron's antiparticle, because charge is conserved, because annihilation produces gamma rays, because those gamma rays travel out of the body in opposite directions, because detectors can measure coincidence events, and because mathematics can reconstruct the source distribution. Remove any one of those facts and the method falls apart. Keep them together and the body becomes, for a moment, readable in a new way. So when we ask how positrons help us see inside the human body, the answer is not just that they light things up, it is that they participate in a carefully designed chain of physical and biological events that turns invisible cellular activity into measurable external signals. They allow us to trace metabolism, blood flow, and molecular targets. They help distinguish active disease from inactive tissue. They can show how a treatment is working. They can reveal patterns in the brain that anatomy alone might miss. And they do all of this by following the same laws that govern their behavior in stars, laboratories, and the wider universe. That is one of the quiet pleasures of this entire subject. The positron never stops being what it is. Whether it is created in a radioactive tracer, a cosmic ray interaction, or a violent astrophysical process, it follows the same rules. It is the setting that changes, and with it the meaning we assign to the signals. In a hospital, the annihilation photons tell us about living tissue. In space, they tell us about energetic cosmic environments. In physics, they tell us about the field structure of reality. The particle itself remains consistent throughout, and because of that consistency, it becomes possible to ask a final, deeper question that has been waiting behind all the others. If the positron can move so easily between theory, experiment, medicine, and cosmology, then perhaps what it really reveals is not only something about antimatter, but something about the world's underlying order and the strange kind of reality fundamental particles seem to have in the first place. By the time we reach this point, the positron has already done far more work than its size would seem to justify. It has entered the story as a prediction from theory, appeared in a cloud chamber as a real particle, forced us to think more carefully about what matter is, showed us that light can become matter and antimatter together, demonstrated that particles can vanish into radiation without breaking any rules of physics, turned up in stars and cosmic radiation, and then quietly made itself useful in hospitals by helping doctors see living processes inside the body. That is an impressive record for something that, in ordinary matter, often survives only a short time before meeting an electron and disappearing in a flash of gamma rays. So it is fair to ask what the positron reveals when we stop treating it as just another entry in the particle list and start taking it as a clue. What does it tell us about reality itself? One answer is that the positron tells us reality is more symmetrical than common sense first suggests. If you looked only at everyday life, you would never guess that the negative electron has an equally massive positive partner waiting in the wings. The world around us is made from atoms containing electrons, not positrons. Chemistry is built around electrons. Metal conducts because of electrons. Molecules form because of electrons. The matter of tables, trees, lungs, oceans, and skin is arranged in a way that makes the electron seem completely ordinary and the positron seem exotic. But that impression comes from the specific history of our universe, not from the deepest form of the laws themselves. The laws appear to allow and even require a stronger symmetry. For every electron there can be a positron, same mass, same spin, opposite charge, opposite lepton number. Not a rough imitation, not a second-rate copy, but a true counterpart. That is already a significant lesson. It means that reality is not built only from the things that happen to be common around us. There is a deeper level at which the universe contains possibilities that ordinary life does not display very often. The visible world is only one way the underlying rules can be expressed. The positron makes that unmistakably clear. It reminds us that familiarity is not the same thing as fundamentality. Just because electrons are common and positrons are scarce in daily life does not mean electrons are somehow more lawful or more real. It means our corner of the universe ended up matter-dominated. The deeper structure seems more balanced than the visible outcome. That brings us to a second lesson. The positron tells us that reality is not made only of durable little objects in the old classical sense. If that were the right picture, the positron would be very awkward indeed. It can be created from energetic processes. It can disappear in annihilation. It behaves as though it is elementary yet not permanent in a matter-filled environment. It seems less like a tiny pebble that has always existed and more like a stable but transformable pattern, allowed by the laws of physics. The electron shares part of this lesson too, but the positron makes it sharper because its life story is often so concise. It appears, it moves, it interacts, it annihilates. The whole sequence shows that what is most real in physics may not be permanent substance, but lawful structure. This is one of the biggest shifts modern physics asks us to make. We begin by imagining that the world must bottom out in tiny hard pieces. We then discover that the better picture is one of fields and excitations. In that picture, a particle is not a miniature marble with a little inside and a little outside. It is a quantized excitation of a field. The positron helps reveal this because it fits so naturally into that language and so uneasily into the older one. Once you think in terms of fields, the existence of the positron becomes more understandable. Once you cling too tightly to the image of little balls, it becomes much stranger. That tells us something about the world. The deeper level of reality may not be object-based in the everyday mechanical sense at all. It may be built from fields whose allowed excitations are what we experience as particles. And then there is the matter of creation and annihilation. The positron teaches that what exists at one moment need not remain in the same form forever, even if the underlying bookkeeping of nature remains exact. An electron and a positron can be created from light under the right conditions. Later, they can annihilate and return their energy to light. Nothing essential is lost, nothing is violated. But the particular particle identities do not endure. This is a powerful correction to the old instinct that real things must be indestructible things. In modern physics, what is stable at the deepest level is not always the particle itself, but the conservation laws and the field structure that govern the transformations, The positron makes that plain because it participates so directly in both directions of the process. This also tells us something important about identity. In ordinary life, we think of identity as belonging to objects that persist through time. A chair remains the same chair, more or less, until it breaks. A book remains the same book even if the page is yellow. At the particle level, identity becomes more precise and more fragile at once. A positron is defined by its quantum properties. It is this because it has a certain mass, a certain spin, a certain charge, a certain place within the structure of the field theory. Yet that identity can end in annihilation. The positron is perfectly real while it exists, but its reality is not based on being an eternal nugget of stuff. It is based on being a lawful excitation with definite properties. This is a subtler kind of existence than common sense usually imagines, and the positron is one of the clearest examples of it. There is another lesson hidden in the way the positron first entered physics. It reveals that mathematics is not merely a shorthand for known facts. Under the right conditions, it can expose parts of reality before anyone has observed them directly. Dirac was trying to describe the electron more correctly. The positron emerged because the theory would not remain internally coherent without a counterpart. That is astonishing when you stop to think about it. Reality turned out to contain something because the mathematical structure of the laws pointed there first. This does not mean that all elegant equations are true, or that mathematics can simply invent the world by good taste alone. Physics is much stricter than that. But it does mean that reality is ordered enough for disciplined theoretical reasoning to discover hidden features before experiment catches up. That fact alone should change how we think about the relationship between mind and world. The positron suggests that the universe is not an arbitrary heap of disconnected events. It has deep structure. That structure can be expressed mathematically, and human beings, with all our limitations and coffee habits and occasional confusion, can sometimes uncover that structure by following logic carefully. The positron is one of the best historical examples of that success. It is a reminder that the world is not only observable, but intelligible, at least in part. Not easy, not obvious, but intelligible. At the same time, the positron also shows the limits of intuition. Nothing in ordinary experience prepares us naturally for antimatter. We do not encounter positrons in daily chemistry. We do not see annihilation at the breakfast table. We do not build instincts around pair production from gamma rays. If physics had relied only on common sense, the positron might have sounded ridiculous. It was theory and experiment together that forced the issue. This teaches a humbling lesson about human understanding. Intuition is useful within the scale of ordinary life, but it is not a reliable guide to the deep structure of reality. The positron is one more place where the universe calmly refuses to match our first mental pictures. It also reveals something about emptiness. Classical thinking treats empty space as a blank stage, a passive nothing in which objects move. The positron belongs to a picture in which empty space is not quite empty in that old way. If particles are excitations of fields, then even the vacuum is the lowest energy state of fields that exist everywhere. Under the right energetic conditions, those fields can produce particle and antiparticle pairs. That means the space through which the positron moves is not just a hollow container, it is part of the physical structure out of which such particles can arise. Reality is therefore less like a box containing things and more like a set of fields whose states include what we call things. The positron helps reveal that shift because it is so obviously tied to the field picture and to pair creation. Then there is the issue of matter and antimatter asymmetry. The positron shows us that the laws contain a powerful symmetry between matter and antimatter, yet the visible universe appears to have broken that balance in practice. We do not see galaxies of antimatter colliding with galaxies of matter at every turn. We do not find positrons sitting peacefully inside ordinary atoms in place of electrons. Something in cosmic history favoured matter over antimatter by a small but decisive amount. The positron therefore reveals not only symmetry, but also the existence of a major unsolved imbalance. It tells us that reality as we observe it is not simply a transparent reflection of the laws in their most symmetric form. History matters, conditions matter. The universe has taken a particular path through its allowed possibilities, and that path includes a leftover excess of matter that makes stars, planets, and people possible. In that sense, the positron reveals that reality is both lawful and contingent. The laws allow a deeper symmetry, but the actual universe does not display that symmetry in an even-handed way on large scales. This is a very modern lesson. We sometimes imagine that once the laws are known, everything important is settled. The positron says otherwise. The laws tell us what is possible and what is allowed. The history of the universe determines which possibilities become common. Reality is not just law, it is law plus history. The positron also tells us that scale is deceptive. Something unimaginably small can matter at the scale of galaxies, stars, and hospitals. A positron emitted from radioactive decay in a scanner can help reveal a tumour. A positron created near a pulsar can contribute to cosmic radiation arriving near Earth. A population of positrons annihilating in the galaxy can leave a detectable signal across vast regions of space. A particle predicted by an equation can reshape philosophy, experiment, astrophysics, and medicine. And that should make us cautious about assuming that the small is trivial and the large is what really matters. Reality is stitched together across scales in ways that are often surprising. The positron is tiny, but it is not minor. There is also a more philosophical lesson here about opposition. In ordinary thinking, opposites often sound like enemies or negations, positive and negative, matter and antimatter, presence and absence. But the positron shows that opposition in physics is not mere conflict. It is part of structure. The positron is not the enemy of the electron, it is its counterpart. Their interaction can be dramatic, yes, but the deeper point is that the universe seems to be built with these mirrored relationships woven into it. Opposition here is generative. It is part of the grammar of the world. The fact that particle and antiparticle can annihilate is only one aspect of that relationship. The more important aspect is that both belong to the same lawful framework. Reality contains mirror forms as part of its design. That design, however, should not be mistaken for a simple visual symmetry like a butterfly wing. The positron is not just a neat duplicate, it has consequences. It transforms how matter behaves when antimatter is present. It opens routes for creation and annihilation. It forces the existence of certain interactions and forbids others. In other words, the symmetry is dynamic. It changes what the universe can do. That is perhaps the biggest lesson of all. The deep structure of reality is not just about what exists, but about what transformations are possible. The positron sits right at the centre of that idea. And then we come to the question of what is real. It sounds almost too large, but the positron earns the right to raise it. Is something real only if it lasts a long time? Clearly not, because the positron may be short-lived and yet is measurable, usable, and indispensable to theory. Is something real only if we can see it directly? Again, no, because the positron is often known through tracks, detectors, and annihilation photons rather than direct vision. Is something real only if it is made of smaller bits? No, once more, because the positron appears elementary. It behaves as though it is one of the basic ingredients, or more carefully, one of the basic excitations permitted by the fields. The positron therefore nudges us toward a more mature idea of reality. A thing is real in physics if it has stable, testable, law-governed effects and fits coherently within the structure that explains those effects. By that standard, the positron is entirely real. That way of speaking may sound dry, but I do not think it is. In fact, I think it is rather beautiful. The positron does not need everyday permanence or everyday visibility to earn its place in reality. It earns it by participating in the universe in repeatable, measurable ways. That is a deeper kind of reality than simple touchability. It belongs to a world where fields can be excited, particles can appear, annihilate and reappear in other forms, and the whole process can still be described with astonishing precision. There is a final angle from which the positron says something very human as well. It shows that the world rewards patience with concepts. The first question sounds childlike. What is a positron really made of? The answer begins simply, and then slowly changes the shape of the question itself. We discover that not everything real is made of smaller chunks in the old sense. Not everything fundamental looks like a tiny object. Not everything that disappears is lost. Not everything rare is secondary. The positron takes a very ordinary style of curiosity and leads it toward a much deeper picture of reality. That is not just a lesson about one particle. It is a lesson about how science works when it is doing its best work. It refines the question without killing the wonder. So what does the positron reveal about reality itself? It reveals that the universe is more symmetrical than the visible world suggests. It reveals that fields may be more basic than particles conceived as little solid balls. It reveals that creation and destruction are better understood as lawful transformation. It reveals that mathematics can discover hidden features of the world before experiment confirms them. It reveals that emptiness is structured, that history matters alongside law, and that something very small can connect the deepest theory to practical medicine and the largest structures in space. Most of all, it reveals that reality is stranger than habit, but not stranger than understanding. And perhaps that is the most reassuring point to leave resting in the mind. The positron is not easy to imagine at first. It is not waiting for us in ordinary experience with a friendly introduction. Yet once followed carefully, it fits. It belongs. The world makes more sense with it than without it. And that may be one of the quietest but strongest signs that science is on the right track. The universe keeps offering things that seem impossible by common sense and then turn out to be necessary once the deeper structure is seen clearly. The positron is one of those things. Small, brief, exact, and somehow large enough to illuminate the architecture behind the visible world.